Hey, welcome to Accelerated Computer Science Fundamentals. I'm Professor Wade Fagan-Olmschneider, and I have a passion for all things data and data structures. Throughout this course, we're going to discover all of the fundamental ideas in computer science, starting with algorithms, as well as data structures, some analysis of the runtime behavior of programs, as well as object-oriented programming. In this course, we'll be using the C++ programming language. We'll spend the first few weeks talking about that programming language and introduce you to the various different aspects of that language. In this course, I tried to design this as a practitioner's view of computer science. In this way, you're going to see computer science through a lot of examples. We have over 100 examples that we're going to go through with you in this course, and I encourage you to follow along. Each example is available to download on GitHub, and all of them are compilable C++ code. So let's begin this journey, and let's get started. Our focus this week is going to be all about getting you ready to program in C++. You'll be setting up a C++ compiler on your computer, and I'll be working with you to understand the feature of the C++ language. At the end of this week, we're going to go through an assignment where you're going to program your very first C++ class. I look forward to seeing the work that you're going to do, and I'll see you in the next video. C++ is a strongly typed programming language. What this means is that every variable has a type, a name, a value, and a location in memory. For example, if we look at the variable declaration below, we can denote that the type is an integer, the name is the name value, and its value is the number 42. In C++, there are only two types of variables that we can have. Every variable is either a primitive variable or it is a user-defined variable. In the primitive variables, there's only 6 commonly used primitive variables. Those are an integer that defines an integer, a character that defines a single character or a single byte, a Boolean which has the value of true or false, a float which stores a floating point number, or more commonly we'll use a double which stores a double precision floating point number. We'll almost always use double over a float. And finally, there is this special type called the void type. We're only going to use the void in context of a function, but the void type denotes that that type has no value. On the other side of things, there's an unlimited number of user-defined types, and we'll define some of our own user-defined types throughout this course. There's going to be two very, very common user-defined types that I want to point out to you right now. One is a string that allows us to build a sequence of characters, and the other is a vector, which allows us to have a dynamically sized array. Notice that to define a string, we'll use stdstring, and this denotes that the string is part of the standard library, and we'll discuss exactly what the standard library provides us and how to use it in just a few lectures. But to really get started, I want to build our very first program. And to do that, we need to understand just one more thing beyond variables, and that is how to start a C++ program. And a C++ program must always start from a fixed starting point. And by the C++ standard, that fixed starting point is the function main. And the function main takes a return value of an integer. By convention, this integer is going to be 0 if the program was successful and non-zero if the program failed. For the first half of this course, we're going to mostly look at example programs, so we expect the very last line of code we see to be return 0, to return a 0 from this program. A lot of this is maybe very, very new to you, and we're just going to dive in and we're going to see lots and lots of real-world programs that you can compile and you can download and you can run yourself so that you can play around with it. So if there's something that confuses you, I urge you to dive in a little bit more. Let's look at this first program, and we're going to look at hundreds of these throughout this course. The very first program is main.cpp in the cpp intro directory. And the very first thing we see is on line 10, we see integer main. This denotes that this must be the starting point of our program. Because we know main is the starting point, we know that everything after main is going to be ran sequentially. So the very first line is int I equals 4 on line 11. And this is going to define our first variable I, and it's going to have the value 4. On line 12, we take the value in I and add 2 to it, and I now becomes 6. On line 14, we define another variable, a character. C takes on the value A. And finally, on line 16, we see a new syntax, standard cout. This standard cout just simply stands for console out, and we want to output these things to the console. The double alligator brackets indicate that we're going to concatenate it. So to the console, we're going to concatenate the variable I, which has the value 6, a space, and the variable C, which has the value A. And then we are going to put a new line. We expect the output of this program to be 6 space A. Let's go over to the console and run this program and see what happens. I've opened up my console and I've moved into the CPP enter directory, and now I can run make to go ahead and compile this code. After this code compiles, I can run /main to run this program, and the output of this program is 6A. This is exactly what we expect. What we did was we used 2 primitive type variables, an integer and a character, to store data in memory and then output them to our console. What's really, really powerful about C++ is when we start building our own custom user-defined data types. And we're going to start building our very first class in the very next lecture. I'll see you there. Last video, we talked about how C++ allows us to create user-defined types. To do this, we use a C++ concept called a class that allows us to associate data and related functionality into a single object. The sample object we're going to use, our first user-defined class, is going to be a cube. Let's see how this works. The big idea of a user-defined type in C++ is the idea of encapsulation. And I think of this as a pill. Something you might take, and inside this pill, you have both data and you have functionality. And we're going to separate the data from the functionality and talk about them individually. Thinking about our sample cube, the data associated with the cube might be something like the length of one side of the cube. And then functionality we might talk about at the cube is going to be getting the volume of the entire cube, which would just be the cube of the length. So in the data side of the pill, I'm going to go ahead and add the variable length. And I'm going to follow Google's style guide. When we have private member variables of a class, I'm going to add an underscore after that variable name just to let us know it's a private member variable, and we'll talk about that more in detail shortly. Functionality, we're going to have a function called getVolume. And here we've encapsulated both the private member data as well as the getVolume function inside of our capsule. And this is the idea of encapsulation. Our class is going to include both that data and the functionality. I mentioned private member data as opposed to just member data, and the one thing that we missed in the pill earlier is that the pill is both divided into functionality and data as well as into protection layers, both private data and public data, private functionality and public functionality. These layers of protection determine who can access what elements of our class. When we have data that's public, that data can be accessed by anyone. Anyone who uses our class, which we're often going to call client code, is any code that imports our class and makes use of our cube or whatever custom data type we have. If a member function or member data variable of our class is public, anyone can access this. The other side of protection is if we declare any of our variables or any of our methods private, that data or that functionality can only be accessed by the class itself. The second idea of encapsulation is when we actually write the source code to implement all of this. We're going to write the source code in 2 separate places. There's going to be a header file which defines the interface to the class, and an implementation file that defines the actual code to run our class. So let's start in taking a look at the header file first. Again, the header file is simply an interface to the class, and it includes the declaration of all of the member variables and the declaration of all of the member functions. But it does not include the implementation of those functions. So what we expect in a header file is going to be something akin to an API, where we're going to define exactly what programmers can call in our class and exactly what our class stores, but not how those things work. Let's go ahead and build ourselves a header file for the cube. Again, here in the CPP class directory, we have cube.h. And in this cube header file, we're going to see our very, very first header file. And I want to point out 4 different features of this header file. The first thing is the very first line of code in the header file is going to be the line of code pound pragma once. This line of code is always present in H files or header files. This pragma once line instructs the compiler to only compile this code once. Even if multiple people use our class, we'll only want the definition of our class to be defined exactly once. The second thing to note is the syntax we use to declare a class in C++. Here you see the keyword class followed by the name of the class itself. So here we have class cube, and followed by the name of the class, we have a curly brace that defines the scope of the class. The last thing to notice about this is the class always ends with a semicolon. The third thing to note is there are 2 different protection regions in the class, and all of the variables and functions are defined within those protection regions. On line 15, you'll see we have the public protection region, and on line 20, you see we have the private protection region. In the public protection region, everything following the public declaration before the private declaration are public variables or public functions of this class. Everything following the private label are private variables or private functions in the class. In this class, we have 3 private functions. We have get surface area, get volume, and set length. We have only 1 private variable in this class. That private variable is length. Notice in this H file, we have not defined how get volume works, how get surface area works, or how set length works. All we've done is declare that these are the functionalities of the class. We need to look at our CPP file to find out how they actually work. In the CPP file, we call this file the implementation file, and it's the code that contains all of the logic to implement our class. Let's take a look at this. In the class CPP file, we've got, again, 3 different areas that we want to look at. The first is we have a pound include that includes a reference to our header file, and then we have the implementation of our 3 functions that were defined in our .h file. The only difference in the definition of these functions from where we saw in the .h file is these functions' name needs to include the name of the class where they're defined in. Here on line 10, we have double cube, : get volume. This means we're going to define the implementation of the cube's get volume function. And cube's get volume returns the length times the length times the length, which is the volume of our cube. Get surface area is the same idea. We have a double get surface area. It's part of the cube class. We define it as 6 times the square of the length. And set length takes a parameter in, double length, and sets that parameter equal to the private member variable length. So set length is going to update our internal variable's length to be equal to the variable that got passed in. Now that we understand how this cube class is built, we can go ahead and build a program using our cube class. To do that, we're going to need a main function, the starting point of all C++ programs, and we're going to need to include the cube.h header file so the C++ compiler can know what a cube object is. You'll see we've included the header file on line 10. We have main on line 12. We declare a new cube on line 13, and then we're going to go ahead and set its length equal to 3.48. I'm going to go ahead and define a variable volume that gets the value of C, our cube's volume. Again, calling that get volume function that we defined in our cube. And on line 17, we finally see out or console out the volume of our cube. So we expect this program to create a cube in memory on line 13, set the length of one side of this cube to 3.48, and then we expect volume, another variable, to be equal to 3.48 times 3.48 times 3.48, which is approximately equal to 42. So the output then is the word volume followed by the number 42. So this is exactly what we expect. Let's go and compile this code and see whether or not we get the results that we expect to get from reading over the code. The code for this video is in the directory cpp class, and then I'm going to run make to compile this code. Once this code compiles, I run /main to run it. And we see that the volume is 42.1442. This is exactly what we expected from the code we looked at on the slides. Awesome. You just saw your very first CPP class, and you were able to make a custom object inside the C++ language. We're going to keep using this cube and learning more about how this cube works inside C++ in the next video. I'll see you there. The C++ standard library, often abbreviated STD or sometimes called the C++ standard template library, or STL, provides us a set of common tools and functionality that we're going to use throughout the course. Let's look at a couple of them. The organization of the standard library is divided up into a number of separate files, and we make use of them by including them in any of our C++ programs. The most critical library that we're going to include in almost all of our programs is the IOStream library. This library allows us to output data both to files as well as to the console itself. And you've already seen us use this. This is stdcout, or console out. A really simple program using this is going to have two features to it. The first feature is every program that uses cout must include #include IOStream. And from there, the main function is likely going to use cout. We do cout by using std, denoting the standard template library namespace, and then :cout. At the end of the line, we see std_indel, which is to denote a new line should be added to the end of our line. What we expect from this program is hello world to be outputted to the screen when we run the program cout. Let's look at if this happens. Moving into the cpp std directory, I'm going to go ahead and run make to build this program. Once we build this program, I'm going to go ahead and run cout. And as you expect, it says hello world. So we see that by using cout inside of a main and including IOStream, we now know how to print anything we want to the console. Let's keep going. Every piece of functionality inside the standard namespace will be prefaced by the std abbreviation. The use of namespace allows us to avoid conflicts with other commonly used names. For example, we talked about a cube class that we're going to be using throughout a number of these lectures, and we're going to want to put that cube class in our own namespace. And that way, other cubes, such as a cube that might be included in the standard template library, won't get confused with our cube. We'll see that in a second. One thing that you may hate doing is typing std::, again and again and again. If you want to just type cout, we have the ability to say using stdcout. By adding this line of code to our file, we can convert typing stdcout into just typing cout. We can look at this in source code to see how this actually works. Here we see that we're doing the exact same thing as our old program, where we have include IOStream here, and we have a main function that outputs hello world to the console. The big difference between cout and cout2 is notice that here on line 14, we're just writing cout, and here at the end of the line, we're writing indel. We can do that only because we've included lines 10 and 11. Lines 10 and 11 indicate that whenever you see cout, we actually mean standard cout, and whenever you see indel, we actually mean standard NL. We'll go ahead and use these using statements off and on. It's often common to see them used with cout because cout is so commonly used. When we use less widely used data structures, you're going to see us preface std::, more and more often. In general, you want to minimize the use of the using keyword because the using keyword is going to make it less clear exactly what you're running. When you say std::cout, everyone knows that's the standard cout. And as you write this code, everyone's going to be familiar with exactly what you're trying to do. Just like before, let's go ahead and run this program and make sure it works. Returning to the console, we see that we've already compiled the code using make, and now we can run /cout2. And cout2, just like the original cout, prints out hello world, everything works fine, and now you know about the using syntax. We're not quite done yet. Let's go ahead and revisit our cube. We can choose any namespace we want for our cube. There's no restriction on the namespace besides the usual restrictions variable names, which it can't begin with a number, and other details that are common across most programming languages. Looking at this program, you're going to notice a few things. First, we have a UIUC cube. Notice that instead of saying cube C, we have UIUC : cube. Here we have c.getLength, which is going to set the length of the cube to 2.4. And then in line 14, we print out the volume of the cube. So c.getVolume is going to print out 2.4 to the third power. This is going to be approximately equal to 13. So we expect a number around 13 to be printed out. And then we see we get another variable, surface area, that is returned by c.surface area. So we're going to ask the cube for its surface area. And the surface area of this cube is going to be a standard surface area formula, so 6 times 2.4 squared, since 2.4 is the volume of our cube, and this number should be around 30 to 35. So when we run this program, we're going to expect that the cube's going to be set to 2.4, and then the first output we see is going to be the volume is going to be printed out to be around 13. The second thing we'll see is the surface area will get printed out, and that should be somewhere around 30 to 35. Let's go ahead and run this program, main.cpp, and see what happens. Again, going back to our console, we see that everything is already built running the make process, so we can go ahead and run ./main. And in ./main, we see the volume is indeed 13.8, and the surface area is 34. This is exactly what we expect for a cube that has a length of 2.4. So we see that we've been able to place the cube into the UIUC namespace. Let's look at how we did that and then wrap this up. As I mentioned, a cube is a rather generic thing. You can imagine there may be multiple different cubes in all of the C++ libraries out there. So because of these hundreds of different cubes that exist, we want to specify that our cube is different than any other cube we might have. So instead of just calling our class cube, we want to be able to reuse this cube and put in a namespace that's separate from any other namespace. As I mentioned, we put the cube into our UIUC namespace. This UIUC namespace is added to the cube class in the H file by simply surrounding everything by the word namespace UIUC and curly braces. So you see this on line 10 and then closed on line 20. So between line 10 and 20, we have encapsulated the cube into the UIUC namespace. That's all we need to do. We need to do a similar thing on the CPP side of thing. Notice line 10 is namespace UIUC with a curly brace. And then here on line 22, after we've finished writing all of the code, we've ended the curly brace. So to put something in a namespace, all we have to do is say namespace UIUC, add curly braces, and we're going to do that inside of both the H and the CPP file. That's it. So you now know how to use namespaces as well as an introduction to the standard template library. We'll start using many different data structures of the standard template library coming up next. First, we want to talk about memory layout and how all of these variables you've been creating are actually stored in memory. I'll see you then. Our focus this week is the C++ memory model. As part of learning about C++'s memory model, you're going to see stack memory, heap memory, references, as well as pointers. In C++, programmers like us have control over the memory and the life cycle of every single variable we create. By default, every variable we've created so far has been stored in something called stack memory. Let's explore what that means. Every variable in C++ always has 4 things. Every variable always has a name, a type, a value, and a location in memory, or what we might refer to as its memory address. Notice that in this example below, we have an integer with the name prime number and its value is 7. So here, the type is int, the name is prime number, and the value is 7. The memory address is not known, but we can explore where this is going to be stored based on how we created this variable. In C++, we can actually get at where the memory is stored by using the ampersand operator, and that's going to return the memory address of a variable. Let's see how this actually works. In this program, we see that we have our main function, and we know our main function is going to be the first thing that runs. Here we define a new variable, an integer, that has a type of int, a name of num, and a value of 7. So we know somewhere in memory, we have enough space to store an integer, and this memory is going to contain the value 7. The first thing we're going to print out to the console is the word value, and then print out the value of the number, and that's 7. The next thing we're going to print out is the address. And the address of the variable is going to be printed out by using ampersand numbers. So we're asking the C++ language to give us the address where that memory is being stored. Because we're going to learn that this is a stack memory address, we're going to expect this address to be a somewhat large number. So this number might be FFFF27242. Notice that this number has a whole bunch of digits to it. It's written in hexadecimal, and it's going to tell us exactly the address of the variable stored in memory. The address is going to differ depending on what system you're on. So when I run this program, I'm going to see a large number, but the exact large number is going to be different than the large number that you're going to see when you run this code. Let's go ahead and run this program and make sure that we see that this variable does have a value of 7 and see that the address that we find is indeed a large value. So let's head over to the console. Navigating into the CPP memory folder, I'm going to run make to go ahead and compile the code. And the program that we just looked at was the address of program. When we run the address of program, we see that the first thing we print out is value 7, exactly what we expect. And then the address is a very large number. Here on this system, it's 7FFFF-C59CA388. So given the length of this number, that's 12 or 13 hexadecimal digits long, we know that this is a very high memory address, which is exactly what we expect of stack memory. Let's look at why this is a high memory address and understand exactly how the memory works in our computer. As mentioned, stack memory is the default memory for all variables in C++ to be placed. So if we haven't done anything special, we know our variable is going to be in stack memory. Stack memory is specifically associated with the current function, and the life cycle of this memory is the life cycle of the function. So if you declare an integer inside of the function, that integer exists as long as that function is still running. When the function finally ends or the function finally returns, then the stack memory for that function is going to be released back to the system. So the life cycle of any variable created inside of a function is exactly as long as the function is being ran. One important property to remember about stack memory is that stack memory always starts from high addresses and then grows down towards the low addresses. So we're going to start at the highest spot in our computer's memory and start adding variables up at the high memory, growing down towards 0. So as we saw in the previous example, we start with a huge address, and we're going to keep moving down and down and down the memory addresses, which may seem a little bit backwards, but system designers chose to start stack memory at high addresses and grow down towards 0. Let's see this example happen when we have two different functions. So the very first function we have is the same main we had in our previous program. We declare an integer named num, and its value is 7. If we go ahead and draw the memory layout diagram, we know the first thing created in our memory is going to be the variable num that has the value of 7. And this is going to have a very, very high address because it's in stack memory. After we've added num to the stack, while main is still running, we're going to jump into the function foo. And the function foo is also going to live in stack memory. And here in this foo function, we're going to grow down towards 0. So the next address we see is going to be the address of X. So somewhere after the address of number is going to be the address of X, which has the value of 42. So what we expect from the console is we expect the first output to say that num is equal to 7. We expect the address of num to be a large value. The third thing we expect to see is that X is going to have the value of 42. And the last thing we expect to see is the address of X is going to be a large number, just like the memory address of num, except for it's going to be slightly smaller, slightly closer to 0, because we see that foo is below where main was running. So main is running, it allocates the memory for num. After num's been allocated, foo is called. So foo's allocation has to happen below the allocation for the main function. We'll notice that it's going to skip a little bit of memory, and that's just the overhead to call the foo function and some C++ internal maintenance. The big idea is we expect num to have a higher memory address because it was allocated first than the memory address of X. Let's go ahead and run this program and see if our understanding and our hypothesis actually check out. Here, looking at our console again, we've already compiled our code, and now I'm going to go ahead and run the program foo. In foo's output, we're going to analyze it and see that the first thing that happens is num's value is 7, and its address is a large number ending with 908. Then X's value is 42. The memory address of X is the same large number, but ending in 8BC. So 9 is a larger number than 8. So we see that the memory where num is stored is 908. The memory where foo is stored is 8BC. 908 is a larger number than 8BC. These numbers both in hexadecimal. So that means that everything about our understanding of how this works makes sense. And you see an example right here. The memory address of num is larger because it's been allocated first. X being allocated second has a slightly smaller value. So we saw this actually happen in real code, and I encourage you to run this program yourself and see how the memory addresses on your computer, they're going to be different because the layout of the memory is going to be slightly different and is randomized. But you're going to see that num will always have a memory address higher because num was allocated first in our program. Awesome. Let's go ahead and talk about how we can actually use these memory addresses inside C++ to help us keep track of all of this memory. One key idea in C++ that makes C++ so powerful is the idea of a pointer. All a pointer is it is a variable that stores the memory address of data. I like to think of pointers as simply an indirection away from our data. So if our data is here, 42, and maybe that's stored as an integer, a pointer is basically going to be a level of indirection away from data. We follow the pointer to where it's pointing to, and we notice that pointer is now pointing to the memory that's storing 42. Pointer itself does not store 42, but the pointer stores the memory address of 42. And if we follow the contents of the pointer, we get to our memory address. Pointers are so fundamental to C++ that the addition of a star to the type of the variable denotes that as a pointer type. Notice here we have an int star as the type. So the type of the variable is int star, the name is p, and the value of what's stored in the integer pointer is going to be the address of the variable number. So we know that there's a type, a name, and a value, and this integer pointer, because it's being declared normally, is going to be on our stack. So now we have an integer pointer that stores the value of where num is actually stored in memory. The very last thing we want to mention is often we're going to have these pointers and we don't actually want to know what the contents of the pointer is. We want to know what the contents of the thing it's pointing to is. And C++ provides us a dereference operator. So given a pointer, a level of indirection can be removed by preceding the variable with an asterisk. So notice this gets a little bit confusing because if you append the type of the variable with an asterisk, it becomes a pointer type. When you actually use the variable, if you prepend it with an asterisk, then that variable will remove the level of indirection. You'll dereference the memory address and get the actual value. So looking at a quick sample code before we look at a full program, here we have integer num7. So we have a piece of memory that's name is num. It has the value of 7. Then we have the variable p, which is a whole nother chunk of memory. It is a pointer, and it points to the address of num. The value in num is a third variable, and this value in num is going to take on the dereference value of p. So we're going to look at p, and once we see what p is pointing to, then we can go ahead and copy that value, 7, into value in num. Notice that the last line here, we do something different. So now that we've copied num into value in num, we say the dereference value of p should be made equal to 42. So we look at p, we follow that to where it's being dereferenced, and we change that value from 7 to 42. And the final state of this program, we have num that contains the value of 42, p that points to the memory address of num, and value in num is going to have the value of 7. One thing I think is really useful is to really look at how all of this actually works in memory and see if we can make sense of it. And as we do it, we're going to uncover a little secret in this puzzle that we see. So in this program, we've got our puzzle.cpp, which you also have in the code associated with this lecture. And we see that we include cube.h. We're using UIUC cube, the standard include file plus the using statement. And now we're going to go ahead and look at the main program and start running this program as though we're a computer. The first thing we do is we create a cube pointer C that we're going to put onto main stack. So the first thing that happens is we're going to allocate an area of this memory for main. So we'll call this main stack. Inside of main stack, we see the first thing we have is a cube pointer. So the type of this memory is going to be a cube star. The name of it is C. And it's going to take on the value of create unit cube. So create unit cube is a function. This function returns a cube star. So here we have a cube. So let's go ahead and create a create unit cube stack frame. This create unit cube stack frame, all of the memory associated with create unit cube is going to go down here, further down in memory. And we create a cube called cube. The type is cube. The variable name is cube. And this is a cube. We set its length to be 15. I'm going to just draw a 15 in the middle of the cube to note it's 15. And then we return a memory address to the cube. So that means create unit cubes, return value is cube. And that means that C points to this stack memory. So I'm going to redraw this to clean it up just slightly. And we're going to see exactly the same thing with a pointer from main's memory into cube's memory. At this point, we have the exact same drawing we drew earlier. And we have main stack frame, we have create units cube stack frame, and we see that the cube is here in create unit cube, and we have a pointer that points to that cube. One thing you'll remember is we said that the stack frame exists only so long as the function is running. So here on line 16, we return the memory address of cube. But because we've returned from that function, we see that this memory is no longer allocated to us. It's not our memory anymore. So I remove the orange box to say that memory has been deallocated by the system. It may not be reused yet. We don't know what's happening in that memory. It may still be our cube, it may not be our cube. But if we run some other function, the operating system almost certainly is going to use the memory that we were just using for create unit cube and that other function, overwriting that with some other data. So what we expect in this puzzle is that when we run some other function, that something crazy might happen to our memory, and our memory is not going to be exactly what we think it should be. If everything runs as defined, we expect that the surface area of this cube is going to be 6 times 15 squared, and the volume is going to be 15 cubed. So they're going to be nice whole numbers, don't have any decimal points, because all we're doing is squaring and cubing 15. And we expect those numbers to 15 cubed to be in the range of a couple thousand. 6 times 225 is going to be in the range of about 1,500. We expect when we print out data for the surface area to be 1,500, the volume to be a few thousand, and we can run this puzzle.cpp and see exactly what happens. We still have all of the old code we ran earlier, and we've already made it, so we can actually see that the compiler's already trying to warn us about something that's happening. So the compiler knows that in our puzzle.cpp, the address of our stack memory associated with local variables is being returned. That means we're already doing something we shouldn't do, and the compiler is helping us out by warning us this is almost certainly a mistake. When we run this code, /puzzle, we see that nothing prints out. And that's because we don't have a cout. So I can go ahead and open up the source code for this, and I'm going to add a little bit of cout to this code. So here on line 10, I'm going to include IOStream, and then I'm going to go ahead and cout the surface area, which is the value A. And I'm going to cout the volume, which is the variable V. So here in the source code, all I've added is 2 cout statements on line 24 and 26 in the provided code, which outputs the value of the surface area and outputs the value of the volume. I'm going to go ahead and save this and close the editor, remake it, and then run this code, /puzzle. Here we see the surface area and the volume are 0. That's absolutely not what we expected, but was a result of that memory being reused by the system for another purpose that just happened to fill up that memory with zeros. So even though the cube should have had a volume of several thousand, the cube actually has a volume of 0 because that memory was overwritten, because we returned a value from a function after the function runs. So the big takeaway from this puzzle is to understand how memory is actually allocated and how memory works, and to never return a reference to a local variable. So you'll rarely experience this, but once you start working with pointers, especially once we get into this week 5 and 6 of this course, you're going to see that this kind of stuff is going to come up, and you're going to always be mindful of exactly what you're doing with memory. Before we wrap this up, let's look at one final piece of code to kind of cement everything together. So here in our final program today, we have a program that sort of does a little bit of everything so that we have a complete understanding of how we expect the system to work. Going with our standard example before, we have a memory allocated called num, and it has the value of 7. And then we expect the first thing to get printed out is num has 7. The address is going to be a very, very large number. The number is going to be slightly different on each system it runs on, but it will always be large. The second variable we allocate is going to be p. P is a pointer that we set to be the address of num. So p, which has the address of num, the contents of p should be this exact number right here, because the value p contains is the memory address of num. So the contents of p will be the exact value of the memory address of num. The memory address of p is going to be right below the memory address of num. So remember, the values start high and grow down. So p's memory address should be slightly smaller than num's memory address. And finally, we want to dereference p. The dereference of p says we're going to follow p's pointer and see what it points to. P's pointer points to 7. So we expect 7 to be the output here. We expect this to be a large number, slightly smaller. So 2300 maybe. So we expect the output to be 7, large number, large number, large number, slightly smaller, then 7 again. The last thing we do is we change the dereference value of p to be equal to 42. So we change num to value to be 42. With num's value of 42, we go ahead and say p is changed to 42, and we print out what num is. So even though we never change num, we change the dereference value of p to be 42. So num's value here is going to be 42 because that's what's stored in memory. So the output we expect to see is we expect to see the number 7, which is the original value of num, a high memory address again, a high memory address that's slightly closer to 0, the dereference value of p, which is 7, the fact that the dereference value changed to 42, and then we expect to see 42 printed out. Let's run this program and see exactly what happens. So here in our final program, we run /main. And /main, we see that the output is 7. We see another very large number. And then we see this number ends in 148. We see this number 148 again, exactly what we expect. Then we said the fourth thing we're going to see is a memory address that is slightly smaller, which is exactly what we see. 148 is a larger value, 140 is a smaller value. The dereference value of p is 7, which we know that because it points to num itself. When we change the dereference value of p to 42, we see that num also changes to 42. So we have both seen in a program and understood exactly how this memory interacts with the system, and we have code that runs that shows this memory happen in practice. This is one of the hardest things to grasp your head around in C++, especially as it comes to pointers. We're going to follow up in the next lecture with heap memory, which includes a lot more pointers. And then after that, we're going to just do an entire video on just puzzles with pointers. So we're going to do a lot of this, and I encourage you to play around with this stuff to really get a grasp on exactly what pointers are, because they're a key idea in C++, and they're going to unlock the true power of all the things we're going to do in C++. I'll see you with heap memory in the next lecture. Heap memory allows us to create memory that's completely independent of the lifecycle of the function, unlike stack memory. Let's see how this works out. In C++, if we ever need memory that's longer than the lifecycle of the function, we have to use heap memory. The only way to create heap memory in C++ is the use of the new keyword. The new keyword is an operator in C++ that's going to return a pointer to the memory address starting of the new data, and not an instance of the data itself. What that means is a new C++ operator is going to do 3 things, and it will always do these 3 things. The first thing is it's going to allocate memory on the heap for a data structure, whatever the data structure is that we're allocating. It's going to initialize that data structure, and it's going to return a pointer to the start of that data structure. We use the term data structure here because we're going to build more and more complicated things beyond just a cube as this class progresses. But for right now, we can think of this as just a simple integer, as a double, as our cube, or anything else. And the only time this memory is ever reclaimed is when we use the delete keyword. So it doesn't matter if we return from the function, doesn't matter if the function ends. The only time the system ever gets back this memory is when we use the delete keyword. So this memory is extremely powerful, but also has an extremely long life cycle if we don't take care to release this memory. So looking at the example of a piece of code, we see that this code is going to actually allocate 2 different variables. The first variable is int star num pointer. So this int star means it's an integer pointer, and its name is num pointer. And this is going to be on the stack. So notice, this is just an ordinary variable. There's nothing special about it. Because it doesn't involve the new keyword, num pointer is on the stack. Its value is going to be a new integer. So new int means that we're going to create heap memory, enough heap memory to store an integer, and that integer is going to be pointed to in our stack memory. So here our stack memory points to our heap memory. The heap memory has enough memory to store an int, and that heap memory is going to exist for the entire length of our program unless we call delete. So let's actually see this code that we just went over actually run. Our main program for this lecture involves a num pointer that allocates a new integer. Then we're going to print out all of the properties of this value. So the first thing we see is num pointer on the stack is going to be a pointer that points to heap memory, and that heap memory is going to be enough to store an integer. If we see out the contents of the dereferenced num pointer, we're going to look at num pointer and follow the pointer and see what is on the heap. Right now, we haven't put any memory into the heap, so we have no idea what's in this memory. It's going to be whatever's laying around from the operating system. So it's going to print out just a mysterious value here on line 13. So the first number it prints out when we run this program is going to be any random integer. We have no idea. The second number is going to be the contents of num pointer itself. Num pointer is an integer pointer, so the contents is going to be the address of heap memory. Stack memory always starts at a high address and grow down. Heap memory starts at low addresses and grows up. So the value in num pointer is going to be a somewhat low number. So this might just be the memory address 1, 2, 3, 4, 5. This number is going to be significantly smaller than a stack memory address. The address of num pointer is going to be a very large address, since this is an address that's on the stack. We then set the dereferenced num pointer to be 42, which means over here in the heap memory is no longer mysterious and unknown, but the heap memory now has the value of 42. So after setting the value equal to 42, num pointer is going to have the value of 42. The memory address of that value doesn't change. It's going to be exactly the same as we see up here. And the address of num pointer is also not going to change. It's going to be the exact address we saw earlier. The only thing that changes when we set the dereference value of num pointer to be 42 is the actual value stored in the dereference memory. So let's go ahead and run this program and see if our intuition and understanding of this code actually matches up with reality. So going into the CPP heap memory directory, we go ahead and run make since it's the first time we're running this code. So we can go ahead and compile this code, run /main. And here in the main, we can go through these lines and see what happens. So num pointer has a mysterious value at the beginning. It happened to be 0. On your system, it may be 0 or it may be some random large value. It just depends on what was in that memory before the program got access to that memory. The second value is num pointer, and that is a memory address, which is a rather small value. So this is what we expect. We said that num pointer points to a heap memory address. That heap memory address is going to be a small number. And then the memory address of num pointer itself is a stack memory address, and it's a large number. When we assign num pointer to 42, num pointer becomes 42, and these memory addresses stay the same. This is C87010, C87010, awesome. And this ends in C1900. This also ends in C1900. So the address of both num pointer and the memory that num pointer is stored in is exactly the same. The contents num pointer is the only thing that changes. So now you've just created your first set of heap memory. Let's go ahead and explore this with diagrams and understand how heap memory interacts so that we have a better understanding of how this all works. So here's a memory layout diagram of a system where we have the stack memory here on our left. And we know this is stack memory because of these extremely large values in memory. Again, the memory address on a certain system is going to be unique to that system, but we know that stack memory is always going to have large values. Heap memory, on the other hand, is always going to have small values, and heap memory is going to start at the small values and grow up, while stack memory starts at large values and grow down. So running the heap1 CPP program, we see the first thing we do is we allocate an int star p equal to a new int. So int star p is going to be allocated here on the stack, and this is going to be a type int pointer named p, and it's going to point to a value on the heap. So it's going to allocate enough room to make an integer. We don't actually have a name for this. We only have a pointer that points there. So this is the dereference value of p. Second thing is cube C. So we have another pointer, a cube star C, and that's over here on the stack. And that value points to a new cube over here on the heap. So now we have 2 stack variables and 2 heap variables. And on line 15, we say the dereference value of P is 42. So we can look at P, follow its arrow, and that value is now 42. And line 16, we say that the dereference value of C, which is a cube, is going to have its length set equal to 4. And then the very last thing we see is we finally see the use of delete operator. So here the first thing we do is we delete C. So when we delete C, we look at the variable C, we see what memory it's pointing to, and we go ahead and delete this memory, giving it back to the system. And then we delete P. And we delete the memory here as stored in the integer, and we give it back to the system. So notice that there's something still left here. We have the stack memory, and the stack memory will get deleted when main returns. But we also have these pointers that point to memory that doesn't actually contain any data for us anymore. So this is a big problem. And there's a solution to this in C++ called a null pointer. So the keyword null pointer, NULL-PTR, which if you come from a C background in C, this was just capital NULL. C++ will use null pointer, and that points to the memory address 0. So null pointer is defined to be pointing to nowhere. It's never going to be used by the system, and it will always generate a very specific kind of error called a segmentation fault if we ever access the null pointers. And you can never delete 0. So it's an address that can't be deleted. It's an address that points to nowhere, and it's an address that's going to generate an error every time we use it. So it's a way to provide some safety so that we don't have the dangling pointers. What that means is if we go look at this slide, what we really want to do is say that C is equal to the null pointer. C is equal to the null pointer as soon as we finish deleting C. So C gets deleted, and then C points to nowhere. Next thing is P gets deleted, and then P should be equal to the null pointer. So P also points to nowhere. The other last bit to note is we've been using this crazy syntax of doing *C with parentheses around it. This allows us to do the correct order of operations, but this gets really, really clumsy, and you're never going to see this in real code. Instead, C++ has a final operator, which we call the arrow operator, that allows us to access the contents of a class when that class is being pointed to. So when the object is stored via pointer, we can access the member functions using the arrow operator. We can say for our cube, for example, C, arrow, whatever we want. This is identical to this kind of crazy syntax of saying we're going to dereference the value of C and then use the dot operator to get at get volume. Instead, we have the C with an arrow operator, which allows us to dereference C directly and get right to the member functions. So let's look at one more piece of code. Here's heap 2. In heap 2, we have cube C1, which is a new cube. So here on the stack, we allocate cube pointer C1. This points to a cube here on the heap. And then cube C2 is allocated here on the stack. And then we point this to the exact same value C1 points to. So notice we have 2 pointers that point to the exact same cube because C1 points to a new cube and C2 points to C1. And now we say C2's cube. We're going to do the arrow operator, which allows us to follow this arrow. It's the dereference operator, but for classes. And we're going to set the cube's length to be 10. And then we're going to go ahead and delete C2. So if we delete C2, we follow its arrow, and we go ahead and delete this data and clear it out. Then we delete C1. If we try and delete C1, our data is not there. We've just deleted something that we shouldn't delete. So because the data is not there, you're going to expect the compiler to give us an error because it's going to try and double free memory that doesn't exist. So we are not going to run these programs right now, though you have the source code. Instead, in the very next lecture, we're going to go over 4 different puzzles, and we're going to puzzle over exactly how heap memory works and run lots of examples in that one. So get ready for some awesome coding, and I'll see you in next lecture. In this video, we're going to do something slightly different. The entirety of this video is all going to be looking at code, and we're going to examine what programs do, kind of puzzly different programs, when we use stack memory, heap memory, and other types of memory. So the reason we do this is to really get an understanding of how pointers work and really challenge ourselves in making sure that we have a deep understanding of how the code interacts with memory, so that when we see examples like this that happen, or have an interview question like this when it happens, or a quiz question, we'll have no problem. So our very first puzzle creates 6 variables right off the top. So here we have 6 variables, int I, j, k, and pqr, where p, q, and r are pointers. Notice the new keyword is not used at all. So because the new keyword is never found, we know that all of this memory has to be stack memory. So I'm going to go ahead and draw the boxes for I, j, and k, as well as p, q, and r, and stick their initial values in it so that we can keep track of it. So I has the value of 2, j has the value of 4, k has the value of 8. P is a pointer and points to I. Q is a pointer and points to j. And R is a pointer that points to k. And now on line 17, we say k is equal to I. So k is going to take on the value that's in I. So k is going to become 2. Now we're going to print out ijk, dereference p, dereference q, and dereference r. So I contains a value of 2, 4, k contains value 2. Dereference p contains 2, dereference q contains 4, dereference r contains 2. So we expect the first output to be 242, 242. Next we see p is equal to q. So p takes on the value of q. So p no longer points to I, but p points to the same place as q. So p is now pointing to j. So I still has the value of 2, j still has the value of 4, k still has the value of 2. The dereference value of p is now 4, the dereference value of q is 4, the dereference value of r is 2. So the second set of output we expect to be 242, 442. Last thing is the dereference value of q takes on the dereference value of r. The dereference value of q is j. Dereference value of r is k. So star q takes on star r. So 4 takes on 2. So now everything should have the value of 2. This is what I got when I ran through this code. Let's see what the computer gets. Going into CPP heap puzzles, running make to compile all of our puzzles, running /puzzle1. First row, 242, 242, exactly what we expect. Then 242, 442, exactly what we expect, and all 2s for the third row. So we've solved this puzzle, and we found that the data we expected is exactly equal to the data we saw on the computer. Awesome. Let's look at another puzzle. Here in the second puzzle, we see that we have the new keyword. So we know that some of this data is going to be on the heap. So I'm going to go ahead and have a section of memory that is stack and have a section of memory that is the heap. So on the stack, we have an integer pointer x, and that's going to point to the new memory on the heap, which is a new integer. we have on the stack int ampersand y. So here we have something we've never seen before. Int ampersand y is giving us something called a reference variable. And a reference variable is something we're going to dive into a lot more next week. But I want to give you a little bit of a preview of it. All a reference variable means is it's going to alias another piece of memory, which allows us to give a name to a piece of memory. So y is going to alias the dereference value of x. What that means is we can say that this heap memory address is called y. So now we have int ampersand y, so reference variable y is going to alias the memory in x. And then we're going to say y is equal to 4, which allows us to alias the memory exactly. If we ask what the memory address of x is, the memory address of x is equal to the memory address of a value on the stack. So we expect this to be a large number. The contents of x is going to be the pointer itself that points to the heap. So we expect the contents of x to be a fairly small number because its value is a pointer to heap memory. And the dereference contents of x we expect to be 4 because we set the dereference value of x, which is the variable y, equal to 4. Next thing we can ask is, what is the memory address of y? Well, the memory address of y is this memory in the heap, so we expect this to be the same small number we saw up here. The value contained in y is 4. And what is the dereference value of a non-pointer? We can't do that. In fact, if we uncomment this line of code, it's going to cause us compiler error. So we see the 5 lines that we expect to print out. It's going to be a large memory address, followed by a small memory address, followed by a number 4, followed by a small memory address again, followed by a number 4. So we want to verify that our program does the exact same thing. And then we're going to see that the 6th line is not going to print out, and we'll look at the source code. We'll uncomment it out and kind of see the error that you're going to get. So let's go ahead and look at this code on the console. Running /puzzle2, we see a large memory address, followed by a small memory address, followed by 4, followed by the same small memory address, followed by number 4 again, and you again see there's only 5 lines. So launching the Visual Studio Code IDE, I'm going to look at puzzle2.cpp. In puzzle2.cpp, I had commented out this line 24. I'm going to uncomment it, save it, and let's run make again and see what happens. And you'll see that we get an error that says the indirection requires a pointer operator. So we can't take an indirection of an integer itself. It's just int y. Because it's not a pointer, we can't dereference a non-pointer. So the only way this code works is had we commented out that last line of code. Awesome. Let's go ahead and look at a third puzzle. Here in this third puzzle, there's no new concepts, so it's something you should be able to work through yourself. I'd recommend working through this puzzle and then checking if your logic agrees with mine. I'm going to go ahead and get started. So here I'm going to create my stack memory. This is an int pointer p and a second int pointer in stack that is q. P is then going to be equal to a new int, so new heap memory is going to be pointed to by p. Q is going to also point to the same, Q is going to take on the value of p, so it's going to point to the exact same memory. And then the value dereferenced by Q is going to be 8, so we follow Q's pointer and put 8 here in this memory. Then we're going to see out the dereference value of p. So the dereference value of p following the pointer is 8. So the first output we expect to see is 8. Now we're going to say q takes on the value of a new integer. So q no longer points to the memory it pointed to before, but points to a new integer in heap memory. The value of dereference q is 9. And then we see out the value of dereference p. Dereference p is 8. Dereference q is 9. So we expect the answer to this puzzle to be 889. Let's see if puzzle 3 gets us that result. Running /puzzle3, we see 889. It's exactly what we expect to see. And if you got that, we're starting to get an awesome understanding of exactly how pointers work and how memory interacts. The very last puzzle adds another little bit of syntax to C++. That is the use of arrays inside a heap memory. Let's look at this code. So here we have int star x on the stack. So we have an int star x. And this points to somewhere. We don't know where yet. The next thing is we have an int size here on the stack, and it has the value of 3. And we say x is equal to the new integer array. So x is now equal to a new integer of size 3. So this new int with the array brackets denotes that we are allocating a sequence of integers. So we have, in this case, 3 integers sequentially in memory stored as an array. We can go ahead and go through this and say I equals 0, I is less than size, so standard for loop that goes through and says the contents of x of I. So when I is equal to 0, 0 plus 3 is 3. When I is 1, 1 plus 3 is 4. When I is 2, 2 plus 3 is 5. So the contents of this array is going to be 3, 4, 5. And then at the very end, because we did a new square brackets, we have to do a delete array as well. So the big thing to take away from this is we may see the syntax where we have an array of memory instead of just a single value of heap memory. We're going to see this very rarely, but I wanted to go ahead and mention it here in this video because it's something that as you look at other code, you may see lots and lots of people make use of an array inside of heap memory. And that use of new int with the array brackets and delete array brackets is a key idea in C++. So if you follow this, you are really a master of C++ memory, and you're ready to really get started on kind of understanding the other part of C++ that makes C++ awesome, which is the use of classes inside the C++ language. So I'll see you next time. Our focus this week is going to be on C++'s approach to object-oriented programming. As part of this, we're going to spend nearly the entire week on the lifecycle of a C++ object. Let's get started. When an instance of a class is created in C++, the class constructor lets us program exactly the initial state of the object that's created. Let's see how this works. In C++, an automatic default constructor is provided for us if we haven't defined any constructor whatsoever. Every class we've seen so far has a constructor. It has the automatic default constructor. All that this automatic default constructor does is it's going to initialize all of the member variables to their default values. Let's look at some code. Here's the cube class that we saw last week. This class has 3 member functions and a member variable length. There's nothing in this class that's a constructor. Because no constructor is present, we have an automatic default constructor. The automatic default constructor, as we mentioned, initializes all of the variables to their default values. What that means is length will take on its default value. So the default value for a primitive type is largely undefined, so we're not sure what the initial length is going to be. If the private member variable was a class, then the constructor is going to define what its default value is. Let's see how we might define a constructor if we wanted to just set up the default values instead of accepting the system default values. To explain what's going on, we want to explain exactly the terminology we're talking about. Earlier we talked about an automatic default constructor. Now we're going to talk about a custom default constructor. The term default constructor defines a constructor that takes in no arguments. A custom default constructor is overriding the automatic default constructor that C++ provides for us. So the simplest constructor we can make is this custom default constructor, and it's going to specify the state of the object when it's being constructed. Because it's a default constructor, it's specifying the default state of the object when no arguments are given. We define a custom default constructor by having 3 conditions being true. We have to have a member function that has the same name as the class itself. So in our cube class, the name of the function is going to be cube. The function needs to take 0 parameters, and the function does not have a return type. So the constructor builds the object. It doesn't return anything back to the programmer. If we look at the name of this function, we know the name of the function is cube. It's part of the cube class, and it takes 0 arguments. If we look at how this looks in code, in the header file for cube.h, we see cube is the custom default constructor. Notice that it has no return type. It's not a double. It's not a void. There's absolutely no return type as part of cube.h. On the other side, cube.cpp is going to define the implementation of the cube constructor. Here we have the cube class defining the cube member function. Because it has no return value and has the name of cube, we know it's a custom default constructor. And here we have the custom default constructor initialize our cube to have an initial length of 1. So effectively, when we create a cube, our cube is going to be a unit cube, where the length of every side of this cube is exactly 1. For our first example here, we can see that we create a cube using the cube class we just defined. Looking at our code, here on line 11 we have our main function. On line 12 we create a cube in stack memory. And on line 13 we're just going to go ahead and see out the volume of the cube. We know that our custom default constructor created a cube that has a side of length 1, so we expect the volume of the cube to be 1. So our expected output is going to be volume 1 when we run this code. Let's check out what happens. Here on the console, I'm going to go into the CPP constructor folder and then go into example 1, running make to build the program, and then running /main to run our program. The output of this program says volume 1. This is exactly what we expected from the code we saw. Awesome. Let's look at doing a little more fancy stuff with constructors. We just talked about a custom default constructor, which had 0 parameters. However, we can also define custom non-default constructors, or just custom constructors, that allow user code to specify arguments to our constructor. For example, we might want the user to specify the length of our cube when they create the cube itself. So here we're going to use the exact same syntax as our custom default constructor, but have additional parameters based on how many arguments we want the user code to pass in. For example, we might have the user pass in its length. Here we have double length being passed in as an argument. Constructors are not unique. Here in this code example, we see that we have a custom default constructor as well as a 1-argument constructor. So a user using our cube class is able to create a cube that has a default value and is also able to create a cube that has a specific length. In our implementation, we see the exact same thing. We see 2 implementations of constructors. Our custom default constructor sets its length to be equal to 1. Our 1-parameter constructor sets the length equal to the length passed in as a parameter. Looking at a second code example, here's another main in example 2. The key difference between the example 1 we saw earlier and the example 2 here is that on line 5, when we declare UIUC cube to be C2, we're calling a custom constructor. This custom constructor is going to be the 1-parameter constructor. So the C++ language is going to go search through all the constructors and find the constructor that has 1 parameter and takes in a numeric value. We see that numeric value is 2. Because we're specifying that the initial length of the side of the cube is 2, we expect the volume to output to be 2 cubed, or 8. So volume 8 is our expected output. Let's see what happens when we run this code. Navigating back to the base directory and moving into example 2, I'm going to run make and run /main. And what we see as the output is the volume is 8, exactly what we expected. Awesome. Let's talk about one important detail before we wrap this up. We started off by talking about the automatic default constructor, the idea that every class in C++ has a constructor of some sort. If any constructor is defined, we don't get an automatic default constructor provided for us by C++. So if we define even a single constructor, the automatic constructor is not provided for us. Even if we define a custom 3-parameter constructor, the automatic default constructor is not going to be provided. So any constructor at all being defined prevents the automatic default constructor from being defined. We're going to see this trend happen throughout all of the different pieces of the constructor that we're going to see throughout the videos this week. Let's look at one example of where this comes into play. So thinking about a combination of our 2 different programs we've seen so far, Here in example 3, we have a UIUC cube C being defined on line 12. Let's look at the cube.h class that's here in the example 3 folder. Here we see that on line 13, the only constructor we have is a one parameter constructor. Because we only have our one parameter constructor, we know that there is no automatic default constructor. And in fact, there's no default constructor whatsoever. There's no zero parameter constructor. So in line 12, when we're trying to call this zero parameter constructor, it's not going to find anything to call it. And because C++ is a strongly typed language, it's going to find this error at compile time. So let's see what the compiler says when we try and run a program where we don't have a constructor that's valid for it to run. Going back a directory, going to example 3 and running make, we see that we get in a compiler exactly what we expect. In main.cpp on line 12, we have a fatal error where there's no matching constructor for the initialization of the cube. We know there's no matching constructor because there is no automatic default constructor. The compiler helps us out a little bit. It did find a constructor, it said candidate constructor is not viable. So it looked at our one parameter constructor and it said the cube with double length doesn't work because it requires a single argument length, but no arguments were specified here in UIUC cube C. The implicit copy constructor and the implicit move constructor are automatic constructors that were built for us, but they also don't fit the bill. So because we defined a constructor and the constructor was not a zero parameter constructor, there was no default constructor, so there was no way for us to construct this cube. C++ gives us an error when we try and compile this, so you may see this error when you program. It's quite lengthy in length, but it tells us really useful information. So that's C++ constructors, and now you know how to set up the initial value of a class. In almost every class we build, we're going to define a constructor so that we can have control of exactly what the initial state of the class is. So we'll see a lot of these. In the next video, we're going to talk about another form of constructor that helps us copy an instance of the object to another instance. I'll see you then. In addition to standard constructors, in C++, a copy constructor is a special type of constructor that allows us to make a copy of an existing object. Let's see how this works. Just like an automatic default constructor, an automatic copy constructor is defined for us if we don't provide any copy constructor whatsoever. The automatic copy constructor is going to copy the contents of all variables. Often, this is going to be acceptable for us. But in some cases, we want to actually define exactly how the copying takes place or possibly share resources between two instances of a class. To define a custom copy constructor, we need two things to be true. The function needs to be a class constructor, so it needs to follow all of the rules for a class constructor, and it must have exactly one argument, and that argument must be a constant reference to the same type as the class itself. A constant reference means here we have a constant cube passed by reference object. Notice the definition. It's part of the cube class, has the name cube. It follows the properties of being a constructor. Looking at some code, we see that we've defined a default constructor up here. This is exactly what you saw last video. And we defined a custom copy constructor down below. This custom copy constructor takes in an object, and the goal is to copy the contents of the object into our current instance. So notice we have an object.length equal to our current length. Since that's the only variable, that's all this function needs to do. In this case, the automatic copy constructor would do exactly this. So there is no need for us to define an automatic copy constructor here, but you're going to find as we build data structures, we need to define custom copy constructors. A copy constructor is invocated automatically in almost every case. Times that it is invocated is when we pass an object as a parameter by value into another function, or if we return an object by value from a function. Initializing a new object from a previous version of an object will also invoke a copy constructor. Let's see examples of all three of these in code. So that we can actually understand what's going on, I've added a little bit of code to our cube.cpp class. In addition to providing the functionality of setting the default constructor having a cube of length 1 and having the copy constructor copy over the contents of the length, I've added a cout statement to say exactly what's been invoked. Whenever we call our default constructor, we'll print out default constructor invocated. Whenever we call our copy constructor, I'll print out copy constructor invocated. This way, when we run our program, we'll see exactly what code is running when we have a set of source code. Here in our first example, we have a main.cpp. Our function main is here on line 15. We create a cube on line 16. Creating a cube is going to invoke a constructor. Here, this is going to be the default constructor. Finally, on line 17, we call foo. Foo takes in a cube as an argument. Because this argument is being passed into a function, we know it has to be copied from main into the foo stack frame. We expect the second call to be made is a call to the copy constructor. So when we run this program, we expect a default constructor to be called first, and then a copy constructor to be called next. Remember, we've annotated our class so we know exactly when these are being called. So let's go ahead and run example 1 and see what happens. Going into the CPP copy constructor directory, moving into example 1, running make, and then running /main. We see the default constructor is invoked, followed by a copy constructor. This is exactly what we expected when we evaluated the code. Let's go take a look at a second example. In this second example, we're going to again start at main and see that cube C2 takes on the return value of foo. So right now, nothing's being created, so we need to take on the return value of foo. So we're going to go ahead and jump up to cube. We're going to go ahead and jump up to foo. In foo on line 12, we have a cube created on the stack. So this cube is going to call the default constructor. And the second thing, we're returning this cube back to main. So similar to our first example, we have an object in foo. We need to copy it over to main so that main can make use of it. So the second thing we're going to see is going to be a copy constructor. Now that it's back in main stack frame, we need to do something with this variable. And here on line 17, we see that C2 needs to take on the value of what's returned by from foo. So we expect a third copy constructor to copy from the main stack frame into the variable C2. What we expect to see when we run this program, 3 lines of output: default constructor, copy constructor, copy constructor. The first copy is to return to the main stack frame. The second copy is to put it into C2. Once it's in C2, we can then work with that variable. Let's see what happens when we run this program. Moving into example 2, running make, /main, default constructor, copy constructor, copy constructor. Awesome. Looking at a third example, we have another program here in main again. And on line 12, we create a cube C. This calls our default constructor. And then on line 13, my cube needs to take on the value of C. Again, because we're initializing this variable, and this variable is taken on the value of C, the value in C is copied into my cube. So we expect the second thing to run to be a copy constructor. So in example 3, we expect a default constructor and then a copy constructor to be called. Let's see what happens. Moving back and moving into example 3, running make, then running main, default constructor, copy constructor. Exactly what we expect. Let's look at one last example that's going to do something slightly different, even though it looks very, very similar. Here in example 4, we have the exact same code as example 3, but somewhat rearranged. So here on line 12, we create a cube. This is going to call a default constructor. In line 13, we create another cube called myCube. Since this is creating a cube and not being assigned from anywhere, it has to call the default constructor. Finally, on line 15, myCube takes on the value of the cube C. We might expect a copy constructor to be called, but here, both myCube and C have already been constructed. They've already been created by different default constructors. A constructor's job is to actually create the object itself and not just copy things between 2 existing objects. I don't expect anything to get printed out here because we're not doing any construction. We're just doing copying. So because it's just an assignment and not a construction, because myCube was already constructed here, unlike the previous example where myCube was constructed at the time it was being assigned, I expect the program to output default constructor, and nothing else. Let's see what happens. Moving back, going to example 4, running make, and /main, we see that 2 default constructors are invocated and no copy constructors. This is exactly what we expected. And to understand why, we'll dive into what it means to have an assignment operator in the next lecture. I'll see you then. Up until now, we've talked about classes having constructors, or ways to initialize the value of the class when it's being created. Now we want to pivot slightly and talk about a copy assignment operator, which defines the behavior of using the assignment operator or the equal sign in code to assign one cube to another cube or one object to another object. Let's see how this works. One thing to remember as we're talking about the assignment operator is that it's very similar to a copy constructor, but it differs in that a copy constructor creates a new object. It's a constructor, while an assignment operator replaces the value of an existing object. So every object in the C++ has to be constructed. It has to be built by some constructor. Once it's been constructed, it can never be constructed again. To change the value of an existing class, a class that's already been constructed, it must be changed through an assignment operation. If the assignment operator is not provided, C++ provides a default automatic assignment operator for us. The assignment operator will try and copy the contents of the values. Simple as that. In many cases, the automatic assignment operator will do everything we need it to do. Only when we have externally allocated resources, such as memory, or we want multiple objects to point to the same thing, do we need to define a custom assignment operator. Let's see how one works. A custom assignment operator is going to require 4 different properties to be true. The custom assignment operator must be a public member function of the class, so it needs to be in the public section. The custom assignment operator must have the function name operator equals. So it's a very specific name, and it has to be exactly operator followed by an equal sign. It has to have a return value of the reference of the class type. So the return value must be a cube by reference if our class is a cube. If our class is a sphere, it must be a sphere by reference. And it must have exactly one argument, and the one argument must be a constant reference to the class's type. Here we see a constant cube by reference object. And the goal of a custom assignment operator is to assign the contents in object to the instance of the class that's being called upon. Looking at our cube class, we now have several different functions. We have our custom default constructor, which we're going to print out default constructor invoke. We have our custom copy constructor, where we're going to print out copy constructor invoked. And now we have our custom assignment operator. Here we see that it returns a cube by reference. Its function name is operator equals. And the one parameter it has is a constant cube by reference. On line 22, you see that we simply copy the value. This is exactly the same as line 17. And then we're going to go ahead and print out assignment operator invoked. So now we know that the assignment operator is invoked as opposed to the copy constructor. So this is the exact same thing we did in the previous video. And we're going to go through a few examples and see what's invoked where. And anytime you have a custom assignment operator, you'll always return a dereference value of this. This is the instance of the class itself, so you're simply returning an instance of the class. Looking at the assignment operator folder, we're going to see the main.cpp is the exact same code we saw in example 4 of the previous lecture. Here we have a cube. We expect that line of code to invoke a default constructor. On line 13, we see myCube is also going to invoke a default constructor. And finally, on line 15, we see that myCube, which has already been constructed, and C, which has already been constructed, are in an assignment operation. So myCube is going to take on the value of C. So we have a assignment operation happen here. Let's see if this works. Moving into the CPP assignment operator directory, running make to compile the code, and running /main. We see 2 default constructors invoked and an assignment operator. Awesome. This is exactly what we expected to see. So there's a small nuance difference between a copy constructor and assignment operator. Their functionality is largely the same, that their job is to copy the contents of one instance of a class to another, but the times they're invoked are slightly different. The invocation of an assignment operator means the object already exists and doesn't need constructed, We're going to explore a lot of these operators as we build data structures later in this class. For right now, we're going to move on and explore more about the construction of a C++ class. I'll see you in the next video. Right now, you understand both how a class exists in C++ as well as how variables are created and stored. I want to take a minute and talk about the intersection of these two topics, where an instance of a variable, any variable, including objects like our cube class, can be stored 3 different ways. They can be stored directly in memory, accessed via a pointer, or accessed by a reference. Let's look into detail about each of these and how they interact with our class. As we learned, by default, all of the variables are directly stored in memory. When we have direct storage in memory, the type of the variable has absolutely no modifier. And the object size in memory is exactly the size it takes up to store. For example, we saw mini cubes. These cubes we talked about being stored in stack memory. We've talked about mini integers. And we've talked about crazy different classes like an HSA pixel. And we've talked about specialized classes like an HSL pixel you see in the assignments. You've also seen us storing things by pointer. We introduced the idea of a pointer when we started talking about heap and memory. And the type of a pointer is the type of the object modified with the asterisk. And a pointer takes on the memory value of another piece of data. And the exact length of that memory address is going to be the memory address width of the system. So for example, I'm on a 64-bit machine, and on a 64-bit machine, the memory address is 64-bit long. And as we learned with heap memory, a pointer simply points to the memory allocated for the object. And we see here's a cube pointer denoted by the star. Here's an integer pointer denoted by the star. Here's the HSLA pixel, again denoted by the star. The star denotes these are each pointers. There's a third way of storing that we've made references to, but we haven't formally defined. That is storage by reference. A reference variable is a special type of variable which aliases existing memory by name and is denoted with an ampersand. So a reference variable never stores any memory itself. A reference variable has no size. It takes 0 bytes of memory to create a reference variable. A reference variable simply refers to some existing memory. And when you create a reference variable, we have to alias that reference variable at the moment we create it. For example, if we have a cube C that we're creating as a reference variable, it must be aliased to the cube, an existing variable, as soon as it's created. Int ampersand I is a reference variable I that's aliasing count. And again, it's taken on this alias as soon as it's being created. Because we're aliasing the memory address, when we change I or change count, we're changing the exact same thing. This is simply an alias to memory that's already created. It gives us a second way of referring to it. Because reference variables have to be assigned when they're initialized, we can see that the line of code HSLA pixel reference variable p semicolon is not a valid line of code because that does not create an alias when it's initialized. And you'll see that if you run this code through a compiler, this code won't even compile. So let's look at why this matters in a real example. So suppose we're going to take our cube class and we're going to make our cube class currency. Our cubes have a value to them based on their volume. So a tiny little unit cube has only a volume of 1, and its value is just 1. So a little larger cube, a cube that has a side length of 5, has a value of this volume of the cube. So 5 cubed is 125, so a cube of length 5 is worth 125 currency. And likewise, a large cube of length 10 is worth 1,000 currency. So every time we create a cube, we're actually creating currency. So we're now playing the role of a banker. And whenever we receive money, we want to actually make sure that we get the cube itself. We don't want to create a copy of this cube. We don't want to do anything else except for transfer the cube to someone else. If we're creating a copy of a cube, we're creating inflation, we're being a bad banker. We want to make sure to understand exactly what's happening to this cube in memory. So what I've done is I've modified the cube class so that we have some output that gives us context on what the cube's doing. So here is 3 different functions of the cube class. The first function that I have here, lines 12 through 15, is a custom 1-parameter constructor. So notice the class name is cube, the same as the class itself. It has 1 parameter. We see it has no return value, so it has to be a constructor. This is a 1-parameter constructor, and it's going to say we created some amount of money. So whenever we call the constructor, we're creating money. The second type of constructor, the copy constructor we have here, takes in a cube by reference. So notice that this reference that we've thrown around before shows up, and this means we're not going to create a new cube when we pass this argument in. We're going to simply have the cube alias to us. And then this alias cube's going to copy into this newly constructed cube. So we see on line 19, we're going to say created, get the dollar amount via copy. So whenever we create new money via copy constructor, we'll see the via copy. So both of these constructors create new money. So we want to be very careful when new money is created. And the third function is the assignment operator. The assignment operator transforms an instance from one value to another value. So this again has the potential to create money. So we're going to say transformed, and we're going to talk about the current volume that the cube has beforehand and the volume it has after. So it's going to transform its old volume into the new volume. So it's actually changing the value of a cube. It's growing or shrinking the cube. So all 3 of these things are concerning because all 3 of these are creating money. So we want to be really, really careful about when these things get invoked in our code. And here we're talking about money, but in computer science, whenever an object is being created, it's taking up memory. There are resources really being allocated when all of these operations are performed. So we're seeing a real example with money, but this is actually a real concern in all programs because resources on a computer we want to be conservative about. So our very first example, we're going to look at what happens when we transfer a cube to another cube by value. So here on line 13, we create a cube of width 10. So we're creating a cube that's worth $1,000. And on line 16, we're assigning that cube to my cube. So because this is being initialized right here, and it's being initialized with an initial value, we expect for a copy constructor to be called. And here we're transferring the cube to another person. But what's actually happening at the end of this program is we don't just have 1 cube, we have 2 cubes because we constructed our first cube and then we used a copy constructor to create our second cube. So I expect that this program is going to create $2,000, which is not what we want to do. But let's go ahead and find out what happens when we run example 1 by value. Going into the CPP memory 2 directory, going into example 1, running make, running /by value. And by value, we created $1,000 and created another $1,000 via copy. Here we created $2,000, certainly something we didn't want to do when we just wanted to transfer $1,000 to another person. So we created some extra memory here. So let's see if maybe using a different memory technique will help us out. The second piece of code we're going to look at is looking at this by reference. So on line 13, we create a cube using the constructor. So we have a cube of $1,000. On line 16, we transfer the money to another person by aliasing the money because we have a reference variable here. So my cube becomes an alias of C. So what happens here is my cube is going to be this cube, as well as C is also going to be this cube. So because we're simply creating an alias of existing memory and not creating any new memory, we expect for the cube to be constructed exactly once and nothing else to happen when we run the by reference program. Let's see if that happens. I've already compiled this code, so I can just go ahead and run /by reference. And by reference creates a single cube worth $1,000. Awesome. So this gets to what we want. We only created a single cube. Now we have two different instances of this variable. Though in doing that, we haven't really transferred anything. We've just aliased two people to owning the same cube. So let's see other techniques and see what else we can do. So this third program in example 1 is going to create the same cube we've had before. So we're going to create a cube of $1,000. And then we're going to transfer this cube via a pointer. So my cube is going to be a new stack variable that is a pointer. So here we have a new variable called myCube. It's a pointer, and it points to the memory that C is defined in. So instead of having an alias where we have two variables that are directly the exact same cube, here we have two variables. One is the cube, and one is a pointer to the cube. So just like the by reference, we expect by pointer to only create one cube that is $1,000. Let's see if that holds true. Running /by pointer, we see that it creates exactly $1,000. Awesome. This is what we expect. Let's try to get something a little more complicated and something more akin to actually transferring money rather than just changing variables around. So up until now, we've just done everything inside the main function. But what we really care about is actually passing money around so that we can have a function like transfer money, that we can give money to somebody else. And similar to three different ways of storing access to variables, we have three different ways that we can pass variables around to functions. We can pass them by value, which is the default way. We can pass them by pointer by creating a pointer that we pass along, or pass by reference, which again is modifying by the ampersand and acts as an alias. It doesn't make a copy. It just makes two different variables alias the exact same memory. So looking at our first function, we're going to again look at by value, by reference, and by pointer. Looking at by value in example 2, we're going to create our cube again of $1,000. And now we're going to send the cube off to transfer the money to somebody else. And here we're sending the cube by value. So the cube is going into this function by value. And we expect, because it's being passed by value, that it needs to be copied from the main function to the send cube function. So we're going to expect here that it's going to send $1,000 or create $1,000 and then create another $1,000 via copy. So we expect to see $1,000 being created and then a second $1,000 being created via copy when we're in example 2 by value. Let's see what happens. Moving into example 2, running make to compile. And now running /by value. We see it creates $1,000 and then creates another $1,000 via copy. This copy happens when we call the send cube function, which sends the cube money somewhere else. Unfortunately, this way actually makes a copy, so you're really sending somebody a copy of your check and not the currency itself. Let's see if we can do better. Here we see a second example where we have a main function creates a cube worth $1,000. And this cube worth $1,000, we are sending using the exact same code as we used in the by value. The only difference we see here, send cube looks the same. When we look at the definition of send cube, it has an ampersand. We're sending this variable by reference. By sending this variable by reference, we aren't copying this variable anywhere. We're just sending an alias of this variable. Because no copies are made, we expect the cube to only ever have been constructed once and only $1,000 should ever be created. Let's find out what happens when we run by ref. Running /by ref, we see it creates only $1,000 exactly once. Awesome. Now let's look at by pointer. Finally, the very last piece of code is going to look a little different than the previous pieces of code. We still create a cube worth $1,000 in memory. And now we send cube, and notice that we're sending ampersand of C. Remember, the ampersand operator before a variable gets the memory address of C. So we're sending the memory address of C into send cube. Because cube is a pointer, we need a memory address. So we're setting it the memory address to get to that cube, and C inside of this function actually points to this cube. So just like what you saw in main, we can manipulate memory as we're sending it through functions by value, by reference, or by pointer. And just for completion, let's go ahead and run this code, and let's see that it only creates $1,000 exactly once, and then the pointer points to this object without actually creating a second version of it. Running /by pointer. Exactly what we expected. It creates $1,000, and it does that exactly once. The final thing to mention is that we can return by all of these different types. We can return by value, we can return by pointer, and we return by reference. When we return by value, we're making a copy. When we return by pointer, we are going to return a memory address associated with that variable. And we return by reference, we are returning an alias to that variable. As we mentioned when we first talked about this, you should never return a reference to a variable that's created on the stack. It's just going to cause problems for you. The compiler hopefully is going to give you a warning, but you'll want to get out of the practice of ever returning by reference when you're returning an internal stack variable. We'll see more about this once we get into data structures. The big idea to take away is we have 3 different ways of storing variables. We can store them directly, we can store them by pointer, or we can alias to some other existing memory. So that is by value, by pointer, and by reference. These 3 different ways of storing data allows us to be really flexible and have a lot of control over exactly how our memory is getting copied around. This cube class provides a great framework for you to go play around with the code and really see how the cubes gets called when it transforms money, when it creates money via copy constructor, and all of the different things you can do with the cube class. So I hope you take a look at it, and we'll go back to talk about more properties of a class in the next video. I'll see you then. At this point, we know an enormous amount about classes in C++. There's one last little bit to add, and that is the class destructor is called as the very last call in the class's lifecycle, and it cleans up the instance of the class. Let's see how it works. Just like all of the other topics about the class we've talked about recently, there is an automatic default constructor that is provided for you for free if you have no other destructor defined. The automatic default destructor only calls the destructor of other member variables, and that's it. It does nothing else special. So if you want to do anything like logging or some cleanup of memory right as your class is being destroyed, you're going to want to define a custom destructor. All destructors are never called directly. Instead, constructors are automatically called by the C++ language when your code's compiled, when the object is being reclaimed by the system. So this happens differently depending on what kind of memory your object's in. If your object's in stack memory, your destructor is going to be called as soon as the function returns. So as soon as the function ends, that stack frame's gone out of scope. We're going to call the destructor on the objects in that stack frame. If it's on the heap, the destructor is only called when that delete keyword's used to reclaim that memory that the object was using. So to create our own custom constructor so we have control over what happens at the end of the class lifecycle, we're going to have to create a member function that follows a specific set of rules, as with the previous class functionality. A custom constructor has to be a member function. The custom constructor has to be the name of the class itself, preceded by a tilde. And all the destructors have to have no arguments and no return type. So there's no ability to change up how we define a custom destructor. There's exactly one way to define it, and the only way to define it is the name of the class itself, preceded by a tilde, with absolutely no arguments. So to really see how this constructor works, let's continue our currency example that we saw in the previous video. Here I've defined 5 different functions as part of the class. So our class is getting loaded with functionality. And the default constructor has 0 parameters and says, hey, I create $1 and I'm going to denote it's a default constructor. The non-default constructor, the one parameter constructor, is going to create a set amount of money based on the volume of it. The copy constructor is going to create via copy. The destructor is going to destroy the money, and the assignment operator is going to transform the money. So every one of the 5 different operations that the class might have invoked on it is going to print out a slightly different line of code. So as we work through a program, we can determine exactly what we expect the program to do and then verify that with the printed output. So let's go ahead and look at a piece of code. So here, starting at main, we're down here at the bottom, and the main's going to call 3 functions. It's going to call cube on stack, followed by cube on heap, followed by cube on stack again. And we'll go through these and see exactly how we think that the cube is going to exist in memory. So the first thing, line 23, we call cube on stack. So we jump up to line 12, cube on stack, creates a cube of length 3. So we have a cube of length 3. So we expect the first line of code to be printed out to be created 3 times 3 times 3 is $27. Then it's going to return it. So the second line is, we don't actually do anything with the class we created. We're going to return its volume. And then because it's on the stack, it's going to get destroyed as soon as we call the return value. So now we're going to say destroy $27. Third line of code's not going to print out until we go into cube on heap. Cube on heap on line 17, we say C1 creates a new cube of length 10. So this new cube of length 10 is going to be in heap memory, and it's going to be worth $1,000. So we're going to say created $1,000. The fourth thing that we're going to have printed out is going to be line 18. Cube C2 creates a new cube. We see there's no arguments here, so it's going to create a default cube. So it's going to create $1 default. And then the fifth thing that's going to happen is going to be line 19. We delete C1. So C1 is the cube that contained $1,000. So we should destroy $1,000. Now we return from cube on heap. Because C2 is in heap memory, we don't destroy C2. C2 is still there. We haven't destroyed it. Because it's in heap memory, we control the life cycle of it. It doesn't get destroyed when the function returns. Line 25 calls cube on stack again, so we expect lines 1 and 2, the 2 lines associated with cube on stack, to repeat. So the sixth thing is going to be create $27. Seventh thing is going to be destroy $27. So we expect the output to have 7 lines. We're going to create and destroy $27, create $1,001, destroy $1,000, create 27, destroy 27. So let's go ahead and run the CPP destructor code and see if that matches up with what we expect to happen. Going into the CPP destructor directory, running make to compile the code, and then running /main, we see 7 lines of code outputted. We see it creates 27, destroy 27. This was our stack memory. We create 1,000, then create 1. This was our memory created in the heap. Then we deleted the $1,000 one. Notice we never destroy the $1 because we've never deleted that memory. Then we create and destroy 27. So this is exactly what we expected. We created the $1,000 in heap memory, and it was destroyed when we called delete. We created the $1 with the default constructor in heap memory. It was never destroyed. So this is exactly what we expected. This hopefully gives you an idea of exactly how all of this kind of interplays inside of C++. And hopefully you're getting an understanding of the life cycle of the class and how these different functions interplay as we make use of the class. The big takeaway with custom destructors is they are absolutely necessary when we have to close or free memory or objects associated with the object in question. If we create a new memory inside the class on the heap, we need to destroy it. If we've opened any files or shared any other memory, then we also need to make sure that we define a custom constructor so we can close the file, remove the shared memory. So anytime we have these shared resources or system resources, it's going to necessitate a custom constructor. So those are the uses you see in custom constructors. And with a custom constructor, you have a really great idea of the entire life cycle of a class, from the constructor to copy and assignment operators, to finally the end of life with the destructor. What's really interesting now is how do we actually use all of this powerful C++ semantics to build awesome things in C++. We'll get started with doing more amazing things with classes next video. I'll see you then. Our focus this week is going to be cleaning up the final bits of C++ that we're going to be using throughout the rest of this course. As part of this, we're going to be discovering the Tower of Hanoi problem. This classical problem lets us build a program to solve what is a pretty complicated problem. So let's get started. A template type is a special type in C++ that can take on different types whenever the type is initialized. For example, the standard vector is a template type. What that means is in the standard vector, we can have a vector of characters, for example, the word Illinois, a vector of integers, for example, the first few prime numbers, or even a vector of UIUC cubes, our custom data type. All of these things represent an array of objects in memory, and it's done through a standard single library called the vector. The standard vector, or SC vector, is part of the standard template library we discussed earlier, and it provides the functionality of a dynamically growing array with a templated type. So there's 5 key ideas of how we're going to use this vector. The first is we're going to include the vector in our program by using #include vector, and that's going to add the ability for us to use the standard vector into that source code file. We initialize a vector by saying std : vector, and we give it the templated type inside of these alligator braces. For example, on the previous slide, we saw inside these alligator braces was character, was int, and was UIUC cube. Once we have a vector initialized, there's 3 functions that we're going to run on this vector. The first is to run the function pushback, and that adds an element to the back of the array. Our syntax would be something like v.pushback of 4. This pushes back the number 4 onto the vector. The second function is the array operator bracket. So for example, we might want to access the first element in our vector. We would say v at 0, since v was the declared vector, and we want to access element 0. This v at 0 is going to retrieve us the 0th element in the vector, so that's going to be the thing that we just added if we've only added 1 element to the vector. The last thing we can do is we can say v.size, which asks the vector what its size is. As we mentioned earlier, when initializing a templated type, the template goes inside of the alligator brackets at the end of the name. So for example, the name of the object we're initializing is a standard vector, and we use these alligator brackets at the end. So this is a standard vector of characters. We can go ahead and see this in source code. So here's a simple program that just uses both the vector and the IOStream library. We've included both of these libraries, and then here on line 11 we have our main, and on line 12 we initialize a new vector that's going to store integers. So we're creating a vector. This vector stores integers. And because vectors are dynamically growing arrays, if it runs out of space, it's going to make it larger. I'm going to draw it exactly how large it needs, but we're not exactly sure what the capacity of that vector is. And next week, we're going to actually explore some detailed analysis to understand what the optimal size of a vector might be. Here, we're going to push 2 to the end of the vector. So here, we're adding 2 to the vector. 3, we're pushing 3 to the back of the vector. And 5 to the back of the vector here. And then on line 17, we're going to see out v at 0. So we're going to look at our vector and look at what's in index 0 and print that to the screen. So in index 0, we're going to see 2 get printed out. Index 1 is here at containing the element 3. And index 2 contains the element 5 and 5. So when we run this program, we expect our output on our screen to be 2, 3, 5. Let's head over to the console and see what happens. I'm going to move into the CPP vector directory and then move into the example1 directory and run make to build this program. then run /main to run it. And here we see the output of 235, exactly what we expected. Let's go and look at a second example. Here's the source code for example 2. We see the same thing, that we're including vector and IOStream as the two libraries we're going to use. So what we know is we're probably going to be using a vector to store some data, and we're going to use cout to output data to the console from the IOStream library. Here on line 11, we find our main. Line 12, we initialize a new vector. This vector is going to contain a lot of objects because we have a for loop here that loops from 0 to 100, and we're going to push back the square of whatever I is. So the first time this for loop runs, I is going to be 0, and I'm going to push in 0 times 0 to the vector. So the first element in the vector is going to be 0. Second time the loop runs, I equals 1. I'm going to push in 1 times 1 to the vector. So the second element in the vector is 1. Third time we run through the loop, I is equal to 2. Element in the vector is 2 times 2, so 4 goes into the vector here. When I is equal to 3, we're going to put 3 times 3, or I times I, into the vector. That's going to put 9 into the vector, then 16, then 25, and so on. So each element of the vector up until the 99th index is going to contain the square of its index. Note that here is element index 0 that contains element 0. Here's index 1 that contains 1 squared, or 1. Here's element index 2 that contains 2 squared, or 4, and so forth. Now on line 17, we can predict what's going to happen when we cout v of 12. V of 12 is going to look at index 12. We know that the value contained in v of 12 is going to be the square of its index. So looking at 12 times 12, that's going to be equal to 144. So we expect the output of v of 12 to be 144, because v of 12 is going to be placed into the vector by pushing it back when I is equal to 12. Let's go ahead and see if this matches up when we run our code. Here in the console, moving out of the example1 directory, moving into the example2 directory, running make, and /main. And here we see the output is indeed 144. So what you've seen here is we now have an ability to create an array-like structure inside C++ called a vector. The vector is slightly different than an array that you may be familiar with in the sense that it grows dynamically. We don't care about its capacity because the capacity is going to grow and shrink as needed. In the next video, we're going to explore a program that makes use of vectors and all the things we know about to build something really awesome. So I'll see you there. Let's explore a classical problem in computer science called the Towers of Hanoi problem. The goal of this problem is to transfer all of the cubes from the leftmost stack to the rightmost stack in such a way that no larger cube can sit on top of a smaller cube. For example, we might start moving the smallest cube on top and moving it over one stack. Made one step in the Tower of Hanoi problem, and we've gotten maybe slightly closer to moving this entire stack from the source here to the destination. Next thing we might want to do is to go ahead and take this purple cube and move it all the way to our destination. The idea here being that we can't put it on top of this yellow cube because that would put a larger cube on top of a smaller cube, something that's against the rules of this game. After moving the purple cube, then we have only two options now. We can't move the orange cube on top of anything because the orange cube is too large. Instead, our options are really to move the yellow cube on top of the purple cube or the yellow cube on top of the orange cube. Here I went ahead and moved the yellow cube on top of the purple cube, which leaves a space to move the orange cube down on top of the empty stack. We can continue this process of juggling these cubes around, with the goal being that we want to slowly move the largest cubes to the right. Notice that here I've stacked up all three of the cubes except for the largest cube in the middle, and now I can go ahead and move the largest cube from where it began to where we eventually want to end it. This process continues, but we want to talk about how we can represent this problem programmatically with code. So what I see here is I see three distinct classes, or three distinct things that we want to represent. The first thing I see is we have these cubes. So we already have a class to represent our cubes. So we're going to use our UIUC cube class to represent a cube. But I see these cubes don't just have a length, they also have a color. So I'm going to go ahead and use a color to represent the cube in addition to its length. So we want to modify the cube class, and we'll do that in just a minute. The second thing I see is I see 3 individual stacks. I see this as this maybe stack at index 0, a stack at index 1, and a stack at index 2. So what we have is we have a series of individual stacks, and all 3 of these stacks are part of something even larger because we need some container to store the stacks. And here, the entire container might just be called the game. So inside the game, we have stacks, and in each stack, we have cubes. And that's the relationship we have between the game, the stacks, and the cubes. Let's go ahead and build a program that creates a number of different classes to represent all of these entities. So in last week's assignment, you've built the UIUC HSLA pixel. You already know how to represent a color. Let's go ahead and see this cube come together. Here I've modified the cube constructor to have a length and a color. And because we've modified the cube's constructor to have a color, we're going to store that color in a new private member variable. So our cube is different than before in the sense that we now have a cube that has both a length and a color. And we have the ability to get a length, set a length, get the volume, and get the surface area. These basic operations have been with our cube the entire time, and all we've done is we've added a color to this cube so we can better represent how the image works. Next, I want to focus on these stacks. Each stack has a series of cubes on top of it. We don't know how many cubes there are. There may be 0 cubes. There may be 3 cubes. There may be 1 cube. And who knows, we might expand this game and there may be 10,000 cubes here in this last stack. We don't know. So because we don't know, an array or a vector in C++ is a great way to represent this. So every single stack needs to contain a vector of cubes so that we can push the cubes onto the stack. The other piece we need, in addition to the vector of cubes, is we need operations to interact with the top of the stack. So notice on every stack, we never care about what's below the top element. We can only move the yellow element. We can't move the yellow and the purple element at the same time. So the only operations we ever have on the stack is to modify the top element by either looking at it or removing it altogether. Here in the stack class, we have 4 public member functions and 1 private member variable. We know it's a stack class because we see class stack here, and this is in the stack.h file. So let's look at the 4 member functions. The first one is to push back. This borrows this terminology we see from the vector, and this pushes an element to the last element on our stack, which is the top of our stack. The second element we see is remove top. That returns a cube by value. So it's going to return a copy of a cube that we created earlier. And we're going to peek top as well. So peek top's only going to return that memory without removing it from our internal data structure. So we can either remove the entire cube or just look at what cube's on top. And then we have our last public member function, which is the size. So the size function tells us how large the stack is. It may be 0 cubes, 2 cubes, 5 cubes, 3 cubes, whatever. Finally, we have this additional friend function here on line 21 and 22. This function is going to be something we see quite a bit throughout this course, and it's always going to take on this std ostream by reference operator less than, and always have an ostream as the first argument and a constant reference of its own type as the second argument. So here we see a friend function that is ostreamed. This friend ostream function allows us to see out an object. If you come from a Java background, this is something like your toString function, that it allows us to write out the output of an object in a textual way. So this way we can actually see what's on top of the stack, and we're going to have to define exactly what that function does in the CPP file. The last piece that I want to build is I want to build the functionality for the entire game itself. So the game itself is going to set up the number of stacks we need. It's going to set up all of the cubes, and it's going to keep track of those stacks. It's going to be the container to hold the 3 stacks. So we'll have this vector to store the 3 stacks, which we'll store as a vector. And we're going to have the constructor create the initial setup of the game. So let's look at the H file. Here in game.h, we see that we're going to use stack.h since we're making use of stacks here in our private member variable. And we have vector. The game class is pretty simple. We simply have a game constructor, which is going to set up the initial state of the class. And we have a solve function, which is going to solve the game programmatically for us. We have the same oStreamFriend function, which allows us to print out the game as an object so we can see out the entire game and get useful information. And then here as a private member variable, we have a vector of stack objects. The final thing I want to show is we have the game itself. So this is game.cpp, and specifically I'm looking on line 17 at the constructor. So the constructor of the Tower of Hanoi game is going to build 3 stacks. So notice we have stack of cubes, and this stack is going to be added to the back of the stacks array. And what's going to happen once this code run is the stacks array is going to have 3 elements in it, and each of those elements is a stack. So this is our stack at 0, this is our stack at 1, this is our stack at 2, and these 3 stacks represent the 3 stacks you see in the game itself. The last 12 lines of code of this constructor just sets up our 4 cubes and pushes the cubes all to stack 0. So here we have our blue cube that has a length of 4, our orange cube that has a length of 3, our purple cube a length of 2, our yellow cube that has a length of 1. So what we have here is the yellow cube, the purple cube, the orange cube, and the blue cube. These are all placed onto stack at 0. So all of these cubes are now at the initial starting point. So when the game is created, the game already has the cubes created. The cubes are on the 0th stack, and the object of solve is to actually solve the game to make sure that the game moves the cubes that are on stack 0 to the very last stack. We haven't seen a main function, so I created a main.cpp that's going to actually run the game. So the goal here is we're going to, here in main.cpp, create a game, game G, and we're going to print out the initial game state. So on line 14, I do cout and say initial game state, and then on line 15, print out G, the game itself. So since we defined our friend oStream operator, we're able to print out the game itself, and that's going to print out information about the game, which I implemented in the game.cpp file that you can check out. Here on line 17, g.solve. This should solve the game. And on line 20, I repeat the previous lines, except for I'm saying the final game state, so I'm printing out G again. And what we expect to see is we expect that G is going to be solved. Right now, I haven't programmed the solve function. So we're going to run this program right now and see this program does create the cubes, and it's going to print out the state of the game. After we see that happen, I'm going to challenge you to solve this puzzle yourself, though we'll go over solutions right after this. But let's see if main runs. Here in the console, I'm going to go into the directory cpp tower and run make to build this program, and then run /main. Here in /main, we see the initial game state consists of stack 0, stack 1, and stack 2. And stack 0 has the cubes 4, 3, 2, and 1 on top of it. In my solve function, I have a small amount of output that just outputs the game itself again. And then here's the final game state, 4, 3, 2, 1, inside of our main function again. I mentioned that our solve currently does not do anything. So the 4, 3, 2, 1 is the exact same state we see in the initial game state. If I open up the file game.cpp, we're going to find our solve function. Looking here at line 17, we have a solve function. And this solve function solves the Tower of Hanoi problem. Here I'm only outputting the game itself, and that was that output that you saw. This here refers to the reference of the game. And your goal here is to finish solving the game. As I mentioned earlier, I'm going to chat about 2 different solutions on how you might go about solving it, but I encourage you before you go and look at those videos, try and play around with this game yourself. Try and solve the game. or at the very least, figure out what strategy you might use, and then you can follow along as we develop a solution. So I'll see you then. Let's look at one solution to the Tower Hanoi problem. When I introduced the problem, I sort of randomly moved cubes around, with the goal being trying to move cubes to the right as much as possible. The first move I made moved the yellow cube on top down to the beginning of stack of 1. And I'm going to denote the move here as 0 moved to 1. The next thing I did was I moved the purple cube that was here to stack 2. This is the move 0 to 2. The final thing I did was move the yellow cube from stack 1 to stack 2. I'm going to denote this as 1 to 2. After I've moved the small subset over to stack 2, I started working on the next cube, the orange cube. The orange cube could move from stack 0 to stack 1, and then we begin moving everything else on top of the orange cube. The first thing that needs to be done is the yellow cube needs to move to stack 0, then the purple cube can move to stack 1, and then the yellow cube can move on top of stack 1 from stack 0. Only now can we move the big cube from the first position all the way over to the position in stack 2. This is our final position for that blue cube, so we're in good shape. Then we can go ahead and move the yellow cube over with the idea that we want to move the purple cube out of the way. But at this point, we can start to see that we're seeing a pattern of moves. The first thing we're going to do is we're always going to move something in spot 0 to spot 1. Then we're going to move anything in spot 0 to spot 2, and then from spot 1 to spot 2. So we see 0, 1, 0, 2, 1, 2, 0, 1, 0, 2, 1, 2, 0, 1, 0, 2, 1, 2. The only difference is we have an arrow at a certain place. So let's go back to this fourth move. Here we just moved a cube from the orange cube from stack 0 and moved it to stack 1. So 0 to 1. And the next thing we're going to do is we're going to move stack 0 to stack 2. So we know this is 0 to 2. But that's not what we did. We actually did 2 to 0. Because in fact, if we did 0 to 2, 0 to 2 would have required us to move this blue cube and put it on top of the yellow cube. So this is not a legal move. And in fact, here, we can't move 0 to 2. The only option we can do is to go from 2 to 0. What we're doing here is we found a strategy of repetitions inside the move order, where our rule is we're always going to go 0, 1, 0, 2, 1, 2, making the legal move at each case. So what we expect is that for the next set of moves, we're going to go 0, 1, and the 0, 1 is going to be in whatever direction results in a legal move. Can we move anything from stack 0 to stack 1? We cannot. Can we move something from stack 1 to stack 0? We can. So we know the arrow must run left. Next thing, we know that we need to go from 0 to 2. Looking at can I move the purple cube to on top the yellow cube? The answer is no. Can I move the yellow cube on top the purple cube? The answer is yes. So we know that it's going to be 2 is placed onto 0. And the very last thing, we know 1 to 2. Here, the orange cube, can we move 1 to 2? Yes. So we know the arrow must go right. We can repeat this process, but let's actually have the program complete this process and see if we solve the game by using this pattern. In the game's class solve function, I have a loop that's going to loop until the last stack has a size of 4. And while the last stack doesn't have a size of 4, I want to continually follow our pattern. I want to make a legal move between stack 0 and stack 1. I want to make a legal move between stack 0 and stack 2. Then I want to make a legal move between 1 and 2. I don't actually have much intuition on why this works, and we'll look at a solution that's much more intuitive as our second solution, but we notice this pattern, and we want to just test whether or not this pattern is actually going to help us solve this problem. The last thing I need to do is I need to write a function that calculates whether or not a move is legal. So if I need to do a movement between 1 and 2, I can either go from 1 to 2 or from 2 to 1. In this case, I cannot put the orange on top of the purple, so I have to put the purple on top of the orange. So I know the only legal move here is to go from 2 and move it to 1. I've defined a new function inside of game.cpp called legal move. And this legal move takes in two indices. These indices are the index of the stack that we want to look at. And let's look at the if statement. So if the stack at index 1 dot peek top, so if I look at the top cube and I just take a peek at it, and then I get the length of that cube. So I'm going to look at the length of this cube's length might be 3. And if that cube is less than a cube that is at index 2, so maybe this has a length of 2. So if 3 is less than 2, then I'm going to move index 1 to on top of index 2. So luckily the statement's false. 3 is not less than 2. So that means I'm going to move index 2 on top of index 1. So I'm going to move index 2's cube onto index 1's cube. So here, after this program runs, we expect a cube to sit on top of a cube. And there's only one legal move. So we're going to continually make these legal moves as much as we can, following the pattern 0, 1, 0, 2, 1, 2. And our program is going to decide which of those two moves are legal and continually run until we find we've reached a solution. I took off one little part at the beginning of legal move, and I wanted just to show you that code real quick. So what we see here is before we even look at the legal moves, we want to do a little bit of analysis to make sure that we're including the fact that we may not be able to peek on top of each stack. So at this point, we said we're going to peek on top of it and see what the top cube is. If the top cube doesn't exist, we're going to get an error because we can't look at a cube that doesn't exist. So here on line 44, I check to see if the stack at index 1 is empty. And if it is, then I know the legal move has to be 2 to 1. Otherwise, I check if the stack on index 1 is greater than 0 and the stack on index 2 is empty. And if that's the case, then the only legal move is 1 to 2. And only if I find that both stacks are non-zero do I go ahead and follow my logic earlier of looking at the top of both stacks and comparing. So the entire function has the logic to check whether or not any of the stacks are empty. And if one of the stacks are empty, we know that the other move has to be valid. If both stacks are not empty, we can actually then compare the top cube. The very last thing you may have seen is we made use of a move function. This function removes the top cube and places the top cube into the variable cube. And then the line 40 goes ahead and pushes that cube onto the stack at index 2. So we're taking the cube off a stack of index 1 and putting it on index 2. And that move function is simply going to look at those two indices and do the move without any checks, because we've already checked what order we need to move them into by how we're calling the move function earlier. So let's see how this entire program works, and let's see if this program actually generates a solution. So let's go over to the console. Here in the console, moving into CPP tower solution. I'm going to run make and running /main to run our program. So what we see is we see a whole bunch of output, and we know we see a whole bunch of output because after every single move, you'll notice in the source code that we print out what the state of the game was. So here at the beginning, the initial game state was stack 0 has 4, 3, 2, and 1, and all the other stacks are empty. And then we go our movement 0 to 1. So we move the 1 that was on stack 0 to index 1. Our second move out of our strategy is to go from 0 to 0, 2, and then 1, 2. And we see this repeats itself again and again and again. And the final game state is amazing. We got the stack 4, 3, 2, 1 that was initially in stack of 0 moved over to stack of 2. So one of the beautiful things about computer science is the fact that this is not the only correct answer. And in fact, this correct answer was something that only came to me as I sort of was working through the problem. And it didn't really intuitively come to me. And this solution isn't the solution that I would approach first. I think this is a solution that's simplest to code, but in the next video, I want to talk about the solution that I find more beautiful and allows you to see another way to solve the exact same problem, and both solutions are going to get the right answer. So I'll see you there. When I think of the Tower of Hanoi problem, I don't think about a series of moves made, but I think of a master plan on what I want to do. And then I divide that master plan into several sub-plans that helps me achieve the goal I'm looking for. What I mean by this is if I look at the Tower of Hanoi problem and I see the 3 stacks, I know my goal is to move the entire tower from stack 0 to stack 2. And in doing that, I know the only way to move this big block is to first move the 3 blocks on top of it here to a spare stack, and then move the big final block to the target destination. And I'm going to use that logic and actually draw out the 2 different pieces of my plan. So here the first piece is to move the entire top part of the stack to stack 1, and move that bottom element to stack 2. And I need to do stack 1 first, or step 1 first, and then I can do step 2 once I have the sub tower moved off from on top of the tower. There's a third step that eventually, once I get the base moved over, I need to move over the sub tower from where it was on stack 1 to stack 2. So at each step, I'm going to take off everything but the bottom layer, move it to a spare spot, then move the bottom layer. So what we know is we need to accomplish step 1 before we can do step 2. We have to remove that entire sub tower that's on top of the bottom cube to our spare spot. Let's think about how we might plan that. To do that, I can just ignore everything to do with step 2, because we know we need to accomplish step 1 first, and we know that whatever is hidden down here is going to be larger than everything above it. So we can, without any concern, put our smaller blocks on top of anything that might be underneath and hidden in this gray area. So my job here is now to move a tower of height 3 over to this middle stack. Well, this looks like another version of the same problem. I need to take these 2 cubes and move it to my spare stack over here, so I can move this 1 cube over to my middle stack. And that's exactly what my plan is here. And then as a third step, move it back together. So let's again just plan on how we might do this first part of moving the stack of 2. Ignoring everything in the bottom 2 layers now, we know everything in those bottom 2 layers is larger than what we're seeing above, so we can look at this problem as only solving moving a stack of 2 things. Well, moving a stack of 2 things should be relatively simple. I move the top layer to the spare spot, I move the purple cube all the way to its intended destination, and for completion's sake, why don't we even just ignore that bottom layer again? And here, I just need to move 1 cube, 1 space. This problem I know how to do. This is a simple move operation. So since I know how to make this move operation, I can just do it. There's nothing on top. There's nothing constraining me. Now I finally made my first move. I did a whole bunch of planning, but at this point I've made my move. And now I can start unwinding our tower. So remember, our original plan was now to move the purple block to its intended target destination only once we removed what's on top of it. We've removed what's on top of it, we can make that movement. And the move made 0 to 2. The very last thing was that third step that we need to move our sub tower on top of our tower to make it the final destination. And that third step we can go ahead and accomplish by simply making a single move, something we know how to do. And now we have our third move. So now we've accomplished the goal of moving this tower of 2 from its initial location to its location that is in a spot that we can start to move our next cube that we've hidden down here. Revealing the next layer, we now have the orange cube that we simply need to move over to the center stack. Because there's nothing on top of it, we can do a simple move. And here we now have the orange cube that's in the correct location. Remember, the next step, though, is to go ahead and move this subtower on top of the orange cube, so then we can move the blue cube from stack 0 all the way over to stack 2, which we can't do right now because stack 2 is occupied. What this means is we can... we can't just move this directly. This is a series of 2 cubes. This is a tower in itself. But we can kind of repeat this process again in saying that, okay, a tower of 2 cubes, everything down here is larger. We don't care about where it's located at. We just know it's larger. And we can divide that problem up. We can completely wind it, unroll it, re-whirl it. And we do this process recursively until many moves later, we finally get the final solution, that we move the entire tower over just as we originally planned. So I think of this as an extremely intuitive solution. The idea that we're going to slowly ignore part of the tower, making only small moves that we know exactly how to do. And by following a pattern, we can eventually get it there. We can eventually get a solution. But let's look at this more mathematically. Let's analyze exactly what's being planned. So instead of looking at the moves that we actually made, let's keep track of the moves we've actually planned. So our plan is to move the source stack. So I'm going to label the stack as a source and the target. The goal here is I want to move everything from the source to the target. To move a stack of 4 blocks from the source to the target required 3 steps. The first step was to remove everything but the 0th block, so blocks 1, 2, and 3, to the spare tile. So we want to move this tower to the spare tile. The second thing was to move that bottom block from the source to the target. And then that third step was we have all of these blocks here on the spare, and we need to move those spare blocks onto the target. The combination of these 3 steps makes it so that we can move the entire tower from the source to the target. Of course, each of these steps themselves may require a number of sub-steps. Following the logic we described earlier, we can ignore that very bottom layer and now just focus on this subtower of 3 blocks. Notice that here in this subtower of 3 blocks, our target for these 3 blocks is different than the target for all 4 blocks. So we wanted to put the 3 blocks into the middle stack so that that bottom tile can move to the far stack. So what happens at each time we add a blinder on top of our stacks, we're swapping the target and the spare. Which stack we call the target and which stack we call the spare is entirely dependent on kind of what round or what height we're on. And we know that the process of converting the stack of 3 from a source to the target involves 3 different substeps: moving this tower of 2 over to the spare, moving this last element to the target, and then moving this tower of 2 back on top of the target. We see these steps outlined here. And of course, those steps then require a tower of 2 to move, and the tower of 2 can move through 3 individual steps. And this process goes on and on and on and on, but we have a pattern to do it. And this pattern repeats the exact same thing every time we go through these steps. What is that pattern? Well, if we look at the very first iteration of that pattern, the moves that we planned to move all of the blocks, so 0 through 3, to the target. In doing that, we need to move blocks 1 through 3, so everything from the start plus 1 to the spare. We need to move the starting location to the target, and then we need to move whatever we move from the source over to the target. So if we take out these numbers and put in variables, we can say that the move to move a source from the start block to an end block to the target requires going from this one past the start to the end. So this is corresponding from moving from 0 to 3. We need to move from 0 plus 1, or 1 to 3 to the spare. Then we need to move 0 to the target. And then we need to move that 1 to 3 to the target. So what we have is we have code that describes an algorithm that we intuited on how we might solve this problem. And this is all we need to know, is we just simply need to plan a move from start to end, and each movement that does that is going to require 3 sub-moves that's going to help us make that move. So here is the game move function, and this move function is going to take in a lot of parameters because we're going to need a lot of information to run our algorithm. As we discussed, we need a start point and an end point. So the starting point initially will be 0, the ending point will initially be 3, and as we move up and down the tower, those start and end points are going to change depending on how our subcalls are made. We also need to know what our 3 stacks are called. So we're going to store a reference to our source, a reference to our target stack, and a reference to our spare stack. And then I've included a 6th variable called depth. This is just going to keep track of how deep we are in the recursion. How many steps underneath the top step have we made? So on line 50, we see out the planning a depth at a certain depth, incrementing depth along the way. So we're planning a move at a certain depth, and the move is going to be equal to whatever move we're about to plan. We output a bunch of stuff that you're going to see on the console. On line 52, the one thing I do want to check before just going into our move pattern is to see if we're moving only 1 cube. And we can see if we're only moving 1 cube by seeing if the start and the end are the same. So if we're moving 1 to 1, that means we're only moving cube 1 because our start and our end is the exact same value. So if our start and our end are the exact same value, if that's the only cube in the range that we want to move, then we can just move the cube directly. So move cube is simply going to move a cube from the source to the target. Then we'll print out the state of the game. Otherwise, we want to follow our pattern we developed. Remember, the pattern we developed says start +1 to end, and we're going to move the source, and we're going to swap target and spare. So notice that we say source, target, spare here at the top. And the bottom we say source, spare, target, swapping the spare and the target. And we go ahead and send depth forward. Second step, so this corresponds to step 1. Step 2 was we move from start to start. So we remove only the initial element. So that element 0 from source to target to spare. And then our very last call, call 3, says we're going to take start +1 to end. And the source of this is actually our spare. So we remember, we put in line 1, we put all of the cubes that were on our source onto the spare. So in step 3, we need to take all the cubes in the spare and move it to the target using the source, the original spot that these cubes came from, as our new spare node. So let's see this program actually work and explore how this program looks when it runs. Going into CPP Tower Solution 2, I'm going to run make. We run /main. And we see the program runs and runs and runs. But at the very end, we see the final game state is 4, 3, 2, 1. That's awesome. So the initial game state here is 4, 3, 2, 1. And then we see there's several planning moves. We plan to move 0 through 3 from a stack at a certain memory address to another stack at another memory address. So from stack 70 to stack A0 using 88 as a spare. We go deeper and we say we want to plan to move 1 to 3 from the source stack, the 70 stack, to the spare stack to 88. So notice these swap back and forth, just as we expected. Then 2 to 3 and 3 to 3. Here now at the planning depth of 3, we're removing the element at height 3 to another element at height 3. We see that only here do we make our first move. We've planned 4 moves, and only then do we make our move, moving this element that was on the 0 stack to the middle stack. So 1 is now on the middle stack. And you can see this process goes on and on and on with lots of planning moves at certain points. Moves when it gets down to the point where we have just a single element in its range. And then here at the final game state, we find that we do successfully move that through. I built this Tower of Hanoi solution to be pretty general, so I hope you play around with it and see how this program works together. You can add more cubes, add more stacks, and as long as you make sure the program knows about exactly what you've added by making sure that you added it to the appropriate data structure, you can then run this program and see exactly how this works when you have more cubes, more stacks, or any of the above. Play around with it, and then I'll see you in the next video. C++ allows us to use the power of templates, just as we saw used in the standard vector when we build our own classes and our own functions. Let's see how this works. A templated variable is declared by using a special syntax before the beginning of a class or the beginning of a function. Looking at the beginning of a class here, before the definition of the class, we have template with an open angled bracket and type name t. The only thing that's going to differ in this syntax is the t. This is the variable name for our template. So here in template type name t, we see that in our class list, we can have things with the type t. When we initiate this list class, we can have a list of integers or a list of strings or a list of UIUC cubes. It can be anything because the templated type can take on another type when the data structure is initialized. Likewise, we can also have templated functions. Here we see the exact same syntax, template type name t, and inside the function itself, we can use t as a type. Here is ta and tb. And this function, this int max, simply looks at a and b, compares them, and returns the largest one. It returns the maximum of those two variables. Let's see how this actually gets instantiated when we run this code and compile this code. Templated variables are actually checked at compile time, which allows for errors to be caught before we even run our program. Consider our max function, which we saw earlier. And when we run this max function, we might call max of 4 and 7. When we call max of 4 and 7, we're asking the program to find the maximum of 4 and 7. Because these variables are both integers, it's going to instantiate a templated version of the max function with integers. So it's going to be read as an int a and an int b are both being compared from the max function. Since we have the if statement that compares whether or not a is greater than b, we're going to check if the integer 4 is greater than integer 7. Since it's not, we're going to go ahead and return b. On the other side of the world, we can think about UIUC cubes. So instead of having a primitive type, we have a user-defined type. And in this user-defined type, we're now comparing two cubes. When we compare a greater than b, we're comparing whether or not the cube of length 3 is greater than the cube of length 6. And this throws an error because we have not programmed the ability for us to find out if one cube is greater than another cube. We haven't overloaded that operator. We haven't defined how a greater than sign might work. And because of that, we cannot compare two cubes. And when we try and compile this code, we're going to find that there's going to be an error. Let's actually see this as an example. Looking at the main program for the CPP templates video, we have our max function that you saw earlier at the very top of our program. And inside main, we're going to call the max function several different times. On line 22, we compare max of 3 and 5. We expect this to output the number 5. Then we compare the max of a and d. Notice the first was a comparison of integers. The second one's a comparison of characters. Between a and d, d is the largest. Next thing is we're going to compare the max of hello and world. This is a comparison of two strings. World is the larger string, so we expect world to be outputted. And then finally, the last line is we're going to compare two cubes. We're going to find the max of cube 3 and the max of cube 6. We argued there is no idea of how to do a greater than operation between two cubes, so we expect this code to not compile. When we remove this one line of code, when we remove line 25, we're going to see that this code should compile and print out 5D and world. Let's go over to the console and see if this works out. Here at the console, moving into this CPP templates directory, I'm going to run make, and we get an error. So we see invalid operand for binary expression UIUC cube to UIUC cube. And this is the A is greater than B. So for A is greater than B, we don't know how to do that for UIUC cube. And we can in fact see where this is specifically called in the next error message. Note an instantiation of function template specified max UIUC cube requested here. So when we did the max of the two cubes, we weren't able to create the templated type because we can't compare A being greater than B. Let's go ahead and edit this code and remove this line 25 so that we can see the rest of this code work. Editing main.cpp. Commenting out line 25. Saving the file. Exiting. Running make. And now running ./main, since make ended up compiling this successfully. And we see the max of 3 and 5 is indeed 5, the max of A and D is D, and the max of hello world is world. So now you've seen how we can create a templated type inside of our own code. And we're going to make use of this as we build more and more complicated data structures. Before then, we want to talk a little bit more about the C++ language. So I'll see you next time when we talk about inheritance. I'll see you then. Inheritance is a powerful concept in C++ that allows us to inherit all of the member functions and the data from a base class into a derived class. What this means is we can create more generic data structures that allow us to build specific and specialized data structures without having to rewrite this logic. For example, if we think about our cube class so far, the cube is really just a specific version of a shape. And there may be some functionality that's true about every single shape. Like every two-dimensional or even one-dimensional shape has a length. And that length can be shared between a cube, a rectangle, and a number of other shapes. So thinking about our base class, the base class is just like our class cube, except here in our shape class, we have a public section, just like the cube class, and a private section. And here the shape class has a constructor and has a one parameter constructor and has a getWidth function that's going to allow us to access this underlying width variable. Notice we don't have getSurfaceArea or getVolume. These are things that are specific to the cube itself. But instead we have only the basic things that are shared between many different shapes. Here in our cube class, we now see we've added an additional few pieces to this class.h file. First, notice that we're now including our base class shape.h. And the way we can declare that shape is the base class is by putting a colon immediately following our class name, followed by public, and then the name of our base class. So here we would read line 14 as the class cube inherits the class shape. And everything we're going to do in this course is going to always be public inheritance. We're always going to see the word public here. And 99% of the use of inheritance is usually public inheritance. After that, we see that we have the definition of functionality specific for our cube. Here we have a cube constructor that has its width and has its color, thinking back from the Tower of Hanoi cube. And on line 17, we have getVolume, which allows us to get the volume of the cube. That's going to be something specific to the cube itself. Because our shape doesn't have a color and only our cube has a color, we're going to store the color here in the private section, but the actual width of the length of the cube is covered in our base class. So we don't need to include a length here inside of our cube. When we initialize a derived class, we must initialize the base class. So you can't simply construct a cube that's been derived from a base class of a shape without constructing a shape as well. So the cube must construct a shape, and by default, the cube is going to use the shape's default constructor. We can use custom constructors by using something called an initialization list. So let's look at the CPP file for our cube. And here in our cube, we see we have the cube constructor, and our cube constructor takes in two parameters. It takes in a width, and it takes in a color. Because we want to give a shape with a specific width, we're going to use the initializer list syntax. So after the end of our function declaration, I have a colon followed by the name of my base class. So I'm asking C++ to initialize the shape class by using the shape constructor that takes in the width as a parameter. And then my logic unique to the cube class is here on line 13. What happens here is the first thing we're going to do is we're going to initialize the shape itself. We're going to create a shape that has a length of whatever width is, and then we are going to add all the cube specific logic. So the shape gets constructed first, and then the cube gets constructed second. There's an interesting bit here on line 16 through 20, where we have a double getVolume function that's inside of cube. And this getVolume function, normally we did width times width times width. Instead, we need to call the getWidth function because the width variable is actually a private member of a different class. It's a private member of shape and not a private member of the cube. Since it's a private member of another class, we don't have access to it. Instead, we need to call the accessor method, the getWidth method, to return that variable for us. And that gets to the idea of access control. When a base class is inherited, we can access all of the public members of the base class, but we cannot access any of the private members of the base class. So anything that's private can only be accessed by the class itself, not even the derived class. That initializer list syntax that we introduced earlier to call a custom default constructor for a base class is used quite a bit in C++, and we can do a lot of awesome things with it. So in addition to initializing the base class, we can use the initializer list to initialize the current class via another constructor. So if we want to delegate all of the work to a different constructor, we can do that. And we can initialize default values and member variables. So initializer list allows us to initialize not just which base class is called, but which secondary constructor is called for us, as well as default values for variables. So for example, if we look at the shape.cpp constructors, we see that in the shape itself, so remember this is the base class, the basic shape constructor, this is the default constructor here, is going to call the one parameter constructor with a width of 1. So what's happening here is the default constructor of shape is using the logic in the one parameter of constructor of shape to initialize our object. And it's specifically passing in, we want a width 1 shape. And in our one parameter constructor, we see we have an initializer list here, and it initializes the private member variable width to the value that's passed in as width. So through the use of initializer lists, we were able to initialize the default constructor with our one parameter constructor, and then in our one parameter constructor, initialize private member variables without ever having to do anything in the code itself. So this is a way to clean up our code and to reuse a lot of our code so we have only a single constructor through the entire process. So let's go ahead and look at the program and see how this works when we run a main program. Going into the CPP inheritance directory, going to run make. And let's look at what main.cpp does. Main.cpp is going to create a cube of width 4 that's purple and print out that we've created a custom cube. This is using the cube that we created that is a derived class of the shape. So if I run ./main, we see indeed we create a purple cube, and we do that through building a shape that has a length of 4 and then creating a cube as a derived class from the base class of shape. As we build more and more data structures, we're going to start building small pieces that we can inherit from to build bigger and bigger systems and more complicated data structures without having to think of all of the logic. So I look forward to working with you guys as we build this thing up. I'll see you then.